morning we're running this QRP 10 watts sitting at our Hamfest, sitting at the tailgate of the truck here with the Icon 703. Tony, over.
USL, my God, they got a good signal there, Howard. What's the QTH?
QTH is in Piscataway, New Jersey. Piscataway, New Jersey, at the Raritan Valley Radio Club Hamfest this morning. And so got a really nice day, probably the mid-70s right now, not a cloud in the sky. So really a great day for a Hamfest, Tony, over.
USL, absolutely, my God. It sounds like you're going to have a good time at the Hamfest as the weather is cooperating. Alan, you guys hang around?
We'll be on and off listening. I'm with the club here that's running the Hamfest, so we're going to be busy helping out with the club table and things like that. But want to at least check into the net and say good morning to you, Tony.
All right, Alan, you are 7:57 into the white mountains of New Hampshire with the QRP setup. Very good signal indeed. Alan, we certainly do appreciate you coming by in support of the net. Have yourself a great day. Enjoy the Hamfest, and we'll catch you on a further net. QSL?
QSL, Tony, thanks again for listening in to the QRP station, and good luck with the net this morning. 7-3 from W2AEW QRP.
All right, Alvin, 73 to you. We'll wish you good luck down there with the Hamfest. Sounds like you got the good weather. We'll declare W2 Alpha Echo Whiskey QRP. On the numbers for Northcard.
Pretty cool. Nice. Nice contact.
K1AJD. November 18 Charlie here.
Hopper Fox. Pretty much located down in Texas. Montgomery, I don't know where that's at. That's just outside Houston. Yeah, north of Houston. Montgomery didn't exist when I lived in Houston. Oh, I think it did. Nobody knew about it. Nobody knew about it. I want to say hi to Mr. Sinclair. Anyway, what's your favorite show? How are you? I'm retired now, taking it easy. I was with Henry Radio for a long time. I left him just last month. Is there an 8K laying around anywhere?
No. Okay. Yeah, let's see, like. There we go. All right, good. A little prettier than the Central Valley. I'm going to try to shoot a picture of the mountain I live on, and that's it off in the distance. That's called Wolf Mountain. And my house is just on the other side of that ridge. And this is Highway 49. It's named Highway 49 because of the gold rush that occurred in 1849. So, okay, here we go. Just a few miles from home, and again, you can see the difference. There's those are called ponderosa pines, so it becomes a lot prettier. All right.
So a friend of mine asked me to show how to do a delayed sweep and use a delaying sweep on a lot of the Tektronix oscilloscopes. So here's a quick example using two different scopes. Starting off with, I've got two signals coming into the scope down here. One is a gating signal, which is just the square wave you see below, and then the other is kind of an RF signal, or I should say a sine wave that's being gated by that gating signal. So we can see a pretty stable waveform. But if we wanted to zoom in to a particular area, that's kind of what the delaying time base is for. So on this scope here, which is an older 485, the controls are right here for the horizontal display. So right now we're just looking at the A time base, and we can adjust that and see different changes in here. But if we wanted to kind of take a closer look at one of these pulses and still have the overall view kind of zooming in, we would use the delayed time base. So in this case, you start off by going to the intensified version, or the intensified display. What that does is it highlights an area of the display, and you can see that highlighted here. And what you can do is you can change that highlighted area by pulling on the horizontal sweep knob and adjusting it. And you can see how we have a different highlighted area here now. And by adjusting this display control, or the delay control, we can delay and look at a given portion of that waveform. So we can increase the sweep speed of the B time base, okay, and narrow up that intensified portion. And as you go to the intensified portion here, we can actually see that intensified. Now what we can do is we can go from the intensified display to what we call an alternate. What the alternate will do is we'll alternate between sweeping the A sweep, which is what we see up here, and just sweeping the area that we see intensified. So if I hit the Alt button, we now can see two more traces show up. There's a trace separation knob here, and if we adjust that, you can see it just adjusts the traces. So really what we've got here now is this intensified portion that you would see on the A sweep is now being shown down here, expanded out horizontally. So if I change that time base again, we can see if I make that narrower or wider, we can actually see the wider area or the narrower area being intensified in. And now you can adjust the delay and look at that waveform at a different portion. For example, if you want to see, I can actually see the sine wave that is in that burst up there. Okay, and as we drop it down, we can actually see the falling edge of the gating pulse and the sine wave being cut off. Okay, right there at the end of that. We kind of zoom out a little bit, we can see that a little bit better. So I can delay over to the next pulse as I work my way across, and I can see that next one kind of popping up there, and you can see it. Okay. Now also there's a way, what this is doing the B time base, if we look at the B triggering controls up here, the B is set in the uppermost position here, which says run, or B runs after delay time. So after we adjust the delay time right here, the B sweep is just running, and that's what we see. It's also possible to tell B to be triggerable, so it can be triggered after the delay time. And what we'll see as we scoot across here, you see how it's jumping? Because that's jumping to the next triggered event, because I'm triggering on the burst itself. So you can actually see how the delay is now jumping, because it's going to delay a certain period of time and it's waiting for a trigger. So it can cause you to have a more stable event. If I keep delaying, it's going to delay across here now, and then boom, jump to the next pulse. So that's kind of what the delaying time base is on this 485 oscilloscope.
Okay, in this brief video we're going to take a quick look through the signal path, or at least the radio signal path of this Ten-Tec 1254 shortwave receiver. That's kind of the basic block diagram. We're going to walk through a little bit through kind of where the antenna goes in here, goes into the first mixer. We'll take a look at the signal as it goes into the radio. Take a look at the LO signal. We really won't be able to look at the signal much through the crystal filter. It's a pretty low level signal at that point. We'll look at that though again as at the second LO and the IF coming out of that. Look it through the IF gain stage, and then after the detector. And we'll just see what those signals look like as we work our way through. So here's the radio here on the bench opened up, and we'll go take a look at that. And we could even peek through the schematic of where things are here if we want to go through there and see where we're poking around. The signal is being generated up here. We're going to use a 10 megahertz signal here that will either be unmodulated, or we'll put some AM modulation on that. We can turn that on or off. And we'll start off by taking that signal and bring it down into the scope. So if we look at it here on the oscilloscope, I can see the signal right here, and with the scope we can actually tell it to go measure what that frequency is. So we can actually see it's pretty close to 10 megahertz. And if we turn the modulation on, okay, there's an amplitude modulation of that signal. In fact, if we slow way down, we can actually look at the modulated envelope here. And let's play with the triggering a little bit, and there we go. There we go. So there's our modulated signal. We can actually see it's about a 1 kilohertz amplitude modulation. Again, if we speed things way back up again, okay, there's our, let's see, let me adjust my triggering here and turn the modulation off. There's our 10 megahertz carrier again. So that signal we're going to take out of the scope here and go into the attenuator here. Okay, and then the output of the attenuator we've got going into the input of the receiver here. Now on the receiver, if we take a look at this, this is our input bandpass filter. This is going to serve to eject images that are above the LO that would appear into the first IF. That's the main function of this this filter. We see here these two variable inductors here, and the crystal sitting right below it, right there, compose the first IF. This is a dual conversion receiver. The first IF is at 45 megahertz. Okay, so we're going to take that IF. That's going to be presented to. I'm sure. Let's kind of back up here. The first mixer is actually inside this can. Okay, so that takes the local oscillator coming from one of these two oscillators here. That gets put in here. Our RF signal gets put into here. This is our first mixer. That the output of that mixer is going to land in this 45 megahertz IF that's composed of this tuned circuit. And then just behind here, that little guy right down there, that's a dual gate FET. That's our first IF amplifier. Okay, that amplifies the signal from this IF and drives the second mixer, which occurs right here. So this is this classic diode ring mixer. Okay, there's a second local oscillator with this crystal right here, and these transistors right here form that second local oscillator that's at 44.545 megahertz, which is actually 455 kilohertz different from the IF, which means we're going to get an IF output at 455 kilohertz as presented through this 455 kilohertz bandpass filter, and then goes in through this IF strip to give us all of the gain at 455 kilohertz. And then coming out the output of the IF chain here, which has got some EGC surrounding it, we'll be able to look at the 455 kilohertz IF and then the amplitude detected output here.
So let's take a look at those signals through the signal path. So we'll take our scope probe and hook it up to the scope here. Okay, and let's see, adjust the scale a little bit here on the scope. And let's start off by, well, probably right about here. Let's start off by looking at, we looked at the input signal to begin with. We really can't look at the signal as it comes into the bandpass filter because it's going to be very low. So we know it's there because we looked at it ahead of the attenuator. So what we'll do is let's just verify what the IF is. So we said that the first IF is going to be at 45 megahertz. So we're looking at a signal that's at 10 megahertz that we can see here. And we're doing some high side mixing here, which means in order to make a signal land in the from 10 megahertz and have it land at 45 megahertz, that means that our LO here is going to be at 55 megahertz. So there's a little test point here to actually look at our LO signal. And if we go look, I just put the probe on that test point. We go over here and look at the scope. There we go. We're basically right at 55 megahertz, give or take a few kilohertz here. So that's our local oscillator. Because the receiver, if we take a look at it, it's upside down. You can see it's tuned to 10 megahertz. So tuning that to 10 megahertz makes the LO land at 55, so that our IF signal lands at 45, which will put it in the filter. For example, if I tune this to another frequency here, let's kind of scoot this up. Now we can kind of see that our LO frequency has changed. So let's go change that back down to 10 megahertz. Let's see, right there. Here's our 10 megahertz, and we're right at 55 meg. Okay, so that first LO, 55 megahertz, is mixing with our input signal at 10, creating an output signal at 45 megahertz that's landing in this first IF chain. And again, we've attenuated the signal going in here, so we're really not going to be able to see it. So the best thing to do then is, okay, we've got that signal coming in, and let's kind of look at where we were looking at that here on the schematic. Okay, our RF input was coming in here, going through our image rejection filter, and this is the first mixer. That first mixer is what's taking the RF coming in from here, and our local oscillator, which comes from these circuits here. It's actually one of these two circuits, depending on what band we're in, will create the local oscillator signal through a local oscillator buffer. That buffer then drives into this mixer. This mixer creates, basically mixes our LO with our RF and creates the IF signal at 45 megahertz that comes down in through this filter. There's the tuned inductor, the two tuned inductors, and the crystal filter, as I showed you on the board. There's our first IF amplifier. Okay, and all these signals are still too low for us to really probe. Plus, this filter is really sensitive to probing, so we'll kind of mess things up there a little bit. So really not a good effective way of probing that. But that output of that first IF is going into this classic diode ring mixer. Okay, the other end of that mixer is being driven by this guy, which is our second LO. Now the second LO should differ from the first IF by the 455 kilohertz, right? Because that's going to create that difference frequency at 455. We can go look at this signal. I'm going to probe this at a point where it's a fairly low impedance point, but it's also not going to be the purest signal. But for the diode ring mixer, it's not really that important. So we go back down to here into the board. These two transistors that we see here and here, that's these two transistors here and here. I'm just going to probe the emitter of that upper transistor there in that cascode stage. And if I can get in there, do it and hold the camera at the same time. So there we go, I'm kind of probed right in there now. And if we go look at this thing here on the scope, okay, so we can speed this up here a little bit. Okay, so we can see that signal. It's not the most linear thing for a couple of reasons. I'm not probing the best point in the circuit. Also, the ground lead is a bit long for these higher frequencies that I'm measuring here. But we can just get the point. In fact, if I go touch the ground lead and move things around, I can make this kind of change a little bit, but we won't do that. But the whole point is we can actually just see the frequency is 44.545 megahertz, which is actually 455 kilohertz off of the IF, which means the difference frequency coming out of that mixer now is going to be at 455 kilohertz. Okay, so we can go back to our circuit here. Now instead of probing that spot, what I'll do is I'm going to pop my little clip lead off the end of my scope probe here. And what we can do now is start to go down into the IF. Okay. And what we'll do is we'll pick a spot here in this IF, probably this IF output right here at 455 kilohertz. Okay. So what I'll do is we're going to have to slow the scope way down here. Okay. Because we're going to be looking at something at about 455 kilohertz. So let me go down here and see if we can probe right down here. Okay, and so now I'm probing right at the output of this IF. Okay, we can kind of barely see that in here. We look over at the scope now, and we can see it's 454.59 kilohertz. That's pretty close to 455. Okay, but you can actually see that IF output. Now that's actually the 10 megahertz carrier that we've got coming out of here that has been converted to 45 megahertz and then to 455 kilohertz. This has all still been unmodulated. So what I'm going to do is let me turn the modulation on. I can actually hear it in the receiver here. And go back and probe that spot again. And we can actually see the modulated RF output here. Okay, you can see the amplitude modulation of that sine wave. Okay, I go back up here and turn the modulation off. Oops. I need 3 hands, so I can actually see I'm unmodulated there. Turn that modulation back on. And let's do that here. And go back here and probe that. You can go see that signal again modulated. Alright. Now if I slow this way down here, and we'll just kind of play with the triggering here a little bit, I should be able to look at the modulated RF envelope here as well. Let's see. And I'm going to have to play with the triggering here. Alrighty. I need 3 hands. So let's see if we can set this guy up here like this. We'll just zoom in a little bit on that scope screen. I'll set this up while I can use my 3rd hand. Okay. Okay. Alright, there we go. So there's our modulated RF output. Okay. Should be able to see that on the scope. Okay. And so that's going to show us essentially what our modulated signal looks like. And then we can also scoot over to our detected output. It should be right here. And let's adjust our triggering, signal level and triggering. And there's our modulated or demodulated output at 1 kilohertz. So that's a quick walk through the signal path of this Ten-Tec 1254 synthesized dual conversion shortwave receiver. Okay, one more look at this Ten-Tec 1254 receiver. So we're going to take a look at, we looked in the previous video at just a simple sine wave modulated carrier, the 1 kilohertz sine wave. But now we've got an antenna hooked up, kind of a rudimentary antenna, but we actually had a signal here at 6.085 megahertz. And so what we'll do is we'll take a look at what that looks like at the IF here. So if we kind of position this thing looking at our scope again, we turn the volume up, we can actually hear the signal. Okay. And if we look at the IF output, okay, I'll turn the volume down here. So what we're looking at there is the modulated 455 kilohertz IF signal. We zoom the sweep speed way up here. Okay, we can actually see we're looking at the 455 kilohertz signal. Okay, kind of scoot all the way up here. If we move some of these little markers around, let's kind of let me adjust my trigger level here. Right about there would be good. And move a cursor here, and right about there. Let's see. And so we go. Just looking at the period of that signal, it's about 455 kilohertz. If we scoot all the way back down again, you can actually look at the modulated envelope there of the RF. Okay, so actually see the modulation. Okay, and then if we scoot over and look at the audio signal after the demodulator, there it is right there. So there's the modulated audio we're getting from the receiver at that frequency. Okay, so a couple of examples of what it looks like with some real-life signals. Okay, here's another quick little low-budget video here. Just tell you a little bit about this little project that I built about 5-6 years ago. Actually, just a little over 5 years ago. It's an equivalent series resistance meter for testing, primarily testing electrolytic capacitors. There's a lot of plans for these up on the internet, and there's also commercial ones you can buy that are well calibrated and everything. And this is really just taking a look at the different schematics that are out there, seeing what other people have done, and just adapting it for what I wanted to build, and also kind of adapting it for the parts that I had on hand in my junk box at the time. There's some lot better designs out there that have got protection for charge caps and stuff like that, but I didn't really care too much to put those things in this design because I'm the only one that's using it. But I'll just walk you through it real quick and we'll show you kind of how it works. So basically there's just a little hex inverter that I use as both a little oscillator. It runs somewhere between 150 and 200 kilohertz, followed by kind of a bunch of parallel inverters here to act as a driver, and that kind of drives the device under test through that little BNC port right there. And we read the resulting voltage and amplify that through this little single transistor amplifier here. And that goes into this little DC restore circuit here, followed by another buffer and a peak detector to generate a DC voltage to render on a little ammeter. And essentially what happens is it acts like an AC ohm meter. It's really all an ESR meter is. So let me show you how I built this thing. I actually built this thing in a little project box. Actually, I found it at Hamfest. You can actually see there was some kind of interconnecting box made in Fairfield, New Jersey. I found this thing at a Hamfest. Look at the price is still there, $2. And when I found this thing, it already had this meter mounted in it. I picked it up a couple years ago, and even before I built this, and said, well, I'll build something into that one day. So this is what I built in it. So we're taking a look at kind of how I built this. It's a real simple little thing. Just turn this around, and basically we could say it's just a little 9-volt battery. There's the power switch, the LED right there. That's the meter, and then here's their circuit. So LM7805, kind of right here that we use as voltage regulator from the 9-volt down to regulated 5. There's our little hex inverter and driver. The little test port right here that I was using with those little sockets before I put this thing into the box. And that little single transistor is my little 20x amplifier. And then the DC restore and buffer circuit for the peak detector is this little analog devices 8032. It's a nice little rail-to-rail op amp that has no phase reversal issues when you exceed the rails and stuff like that. So I made a nice thing for that. This whole thing is just like on a perf board, all kind of just point-to-point wired with kind of stiff wire and things like that. We kind of take a peek underneath here. You can kind of see, there's really nothing special about the construction. And then the pot for doing the zero adjustment. So I'll kind of show you how we use this thing, and how I use it to find some bad caps in an LCD monitor I was working on. So I'm going to put the camera down here on the table. Okay, and we'll go look at how we use this thing. So first thing we'll do is just show you how you kind of start off with using it. You want to kind of zero it just like you do with any other ohm meter. So I'm going to stick a BNC cable on here, and I'll lift the camera back up. So if I turn it on, you can see the little green light come on there. Boom, it's on. And what I'm going to do is just connect up to this little resistance substitutor box here, so you can kind of get an idea of how this is calibrated. Unlike the units that you find out on the market that you can buy, a lot of them are really very well calibrated. This one is just kind of rough, which is all I needed to do to figure out if I had bad caps or not. So we can see with this thing dialed in at 0 ohms. We're pretty darn close to being zeroed, so I can kind of adjust the thing here and zero us out. So that would tell us that I've got less than an ohm of resistance connected, whether it's just a resistor or in this case even a capacitor. And we notice if I dial this up, I'll see if I can get both these in screen. So there's 1 ohm resistance, and 2, and 3, 4, 5, 6, 7, 8, 9. So 9, and then if we go to 10 ohms, there's 10 ohms of resistance. So 10 ohms is about half scale. And we go to 20, 30, 40, 50. So it's about a 50 ohm scale. And certainly, typically anything over just a few ohms at most is it would indicate, typically a bad cap. So if we disconnect my resistance substitution box here, and what I'm going to do is connect up a set of test leads here, and we'll go look at a couple of capacitors. So here we go. So let's look at this guy. is a 470 microfarad cap, just an old cap I had laying around here, but thought it'd be a good one to use because I have some 470 microfarad caps that I just pulled out of a power supply that are bad. This one, you know, it looks kind of grungy, and it's got some goop on it from wherever it was installed last. I don't know where I salvaged this thing from, but it measures good on the capacitance meter. And if we go and measure this thing here on the ESR meter too, so I can do this with one hand, we'll connect up one lead and the other lead here. Boom. Now if we look on the ESR meter, boy, that's pretty darn close to a short, which tells me that there's very little equivalent series resistance in this cap, so that's a good thing. So let's go take a look at those caps that I yanked out of the LCD monitor recently. So let's go pull one of those guys over here. We take a look at this cap. So it's another 470 microfarad cap. Okay, the 16 volt 470 microfarad cap. Now if the camera can pick this up, if I get close here, kind of see that the top of that's a little bit bulged, and that's kind of a dead giveaway that capacitor is kind of going bad in most cases. I can't really see too much on the bottom of this one that it might be bulged, but let's look at it. I pulled a second one out on the same board. So if we look at this one, you can't really tell too much that it's bulged on the top, but you certainly could see the bottom of this one is bulged out a little bit. So if we take a look at these guys on the ESR meter, we'll find that even though they're the same value as that 470 microfarad cap I was just looking at, let's go clip them into this one here and see what we've got. So let's clip this guy right on here, and looks like these clips aren't going to work really well for these leads, but let's see what we can do. So I'll clip one of them on there, and I'll clip the other one on here. Okay, and now if we go look at the meter, okay, oh boy, that guy's sitting right about where the 10 ohms was. So that's most certainly a bad cap. I mean, any of these 470 microfarad caps should really be, you know, somewhere under an ohm or less typically, even if they're really small like that cap is. So so that certainly indicates that that was a bad cap. And the nice thing about the design of this one is that it only puts about 200 millivolts peak to peak across the capacitor, which means you can actually test these caps, and you know, for the most part in circuit, because the voltage is not large enough to turn on any diodes or other junctions and things like that. So a lot of times you can just very quickly go through and test these capacitors while they're still in the circuit board just by probing them and looking for something that's very close to 0 ohms. And if you see something that is like this one that is well over or close to 10 ohms, it looks like, that tells you that's probably a bad cap. So anyway, that's a quick little tour of this little ESR meter that I built and how you can use it to look for bad caps. Here's a quick little video that shows the ability of different types of scopes to catch infrequent little glitches, and it's been one of the kind of Achilles heels of kind of low cost, you know, kind of entry level bench type digital scopes, that they typically aren't really good at that because the rearm time between triggered events is so long. You could really miss something. So this little test board's generating a digital signal with infrequent little glitches. And here's a typical entry-level, you know, bench type, or I should say a bench type scope that's looking at this. This is actually a little Tektronix TDS 2014, very low-cost digital scope, and pretty typical of what you would see in terms of a waveform writing rate. They say that these scopes really can't even match the writing rate of an analog scope, so let's look at that same signal here on an analog scope. And if we look at this on the analog scope here, this is an older Tech 2465A. Even if we turn the intensity up here, you know, everything looks kind of normal. And I got the intensity cranked all the way up here now. I can't really see any unusual glitches or anything like that. Now back in the mid to late 80s, Tektronix recognized that the writing rate even of these scopes could be improved for looking at catching infrequent glitches and single shot events, and developed an oscilloscope that had a tube called a microchannel plate CRT, an electron accelerator, if you will, electron multiplier at the face of the CRT. That was put into a couple of scopes, including this 2467 here. So it gives it a very, very fast writing rate. So if we turn the intensity up here, now I can actually see that little infrequent event. Kind of move in there. You can actually see that little infrequent event occurring right there in the middle of that big pulse. You can also see a real narrow little glitch going on in the middle of that first pulse. This is the kind of thing that even, you know, something that even most analog scopes couldn't see, but this special CRT allows you to see that. kind of fast forward to today. Let's kind of scoot over here to this scope here. This is a Tektronix 4000 series bench scope, and with a very, very high probability of intercept of catching these infrequent glitches, and these little glitches are easily seen, you know, on this scope here as well. And the beauty of these things now too is that not only can we see them, but we can also trigger on them. So for example, that little glitch right there, call that a runt pulse, a pulse that doesn't reach full amplitude. So I can change my trigger type. Right now I'm showing a trigger type as an edge. I can go change that to a runt trigger. Scroll that up. I went a little too far. Let's go back to runt. Boom. Okay, now I'm doing the runt trigger. Turn this off, and now I'm literally triggering right on when that occurs. Let's kind of scoot this over and kind of see the whole waveform there. Let's move that over there. There we go. So I can literally trigger on that event. Not only can I see it, but then I can trigger on it. So just one quick example of, you know, the discovery capability of being able to see these infrequent events and then be able to isolate them, trigger on them, capture them, so you can go analyze them. Okay, this video is to document a little project that I did with a local ham radio club. Went to one of the meetings there and talked about a couple of ways you could use your oscilloscope to monitor your RF output of your ham radio transceiver. So this was a little project that I built here. Talk about you know, what it is and how to use it. So I built this thing to go along with my little ICOM 703 QRP transceiver. Got right here. And let's take a look at what this thing is. I'll just turn this thing over here, kind of see how we built this, and we'll talk about the schematic here. So really a very simple little thing, and just to demonstrate some capability that anybody can do in their lab. So here's the schematic for this thing here. And there's really two parts to it. We have an RF input that comes in, RF output comes out, and literally the signal just loops through here. So from an RF standpoint, there's really nothing going on other than just passing through this device. And there's really two halves to the circuit. Right here is we just have a simple voltage divider. And again, the values are really not very critical. I did a ratio of, you know, a little less than 100 to 1. A voltage divider here, you want to size these resistors so that you can handle the power that you're putting through them, or actually what they're going to be sensing. If you're doing a 100-watt transceiver, they just don't have to be 100-watt resistors. You just need to calculate the power that you would do for each of those. And then we're just going to AC couple that sampled RF signal, that attenuated RF signal, into the scope. Pretty simple. The other half is a little AM detector or RF detector circuit, and there's dozens of different variations on this design. You find them all over the internet, RF detector probe type things. And again, with the RF signal, we're just AC coupling into a pair of diodes to essentially rectify that signal and drop it onto this 1000 puff capacitor, a little bleed off resistor here, and then also coupling that into the scope. So this signal here would give us essentially the RF amplitude, or an AM mod, whereas this signal will actually show us the RF carrier itself. If we look at how we built this thing here, we can see it pretty easily. The RF, you know, in and out is right through here. Here's my little resistor divider between the 47k ohm resistor and the 1k ohm resistor down, or the 690 ohm resistor here. AC coupling into this guy. So that blue coax is going off to one of the channels of the scope to look at the RF output. And then this side here, we can see I've got my little 10 picofarad cap here, coming to these 1N34A diodes, sitting kind of down underneath here. There's the 1000 puff cap to ground, bleeder resistor, and then off to the other BNC, the little tan colored BNC there going off to the scope. So I've got the transceiver here. There we go, sitting in AM mode, that's 7.2 megahertz, right in 40 meter band, and I'm coupling into a dummy load there, so we're not going to be transmitting out over the air. We just follow the coax leads out to the scope, and I can see the two scope channels right here. So remember the blue lead right here on channel 1, that's the one from our RF sampler. So if I take the microphone and key it up, I can see the RF envelope very easily, okay, on the scope. If we go through here, and let's turn the speed of the sweep way up here, okay, we can actually see the RF carrier. Okay, so we can actually look to see if there's any distortion on the carrier. If I speak into the microphone, we can actually see the amplitude modulation of that carrier. I've got the transceiver in AM mode. If we slow the scope back down again to, go down to 1 or 2 milliseconds per division, and now if we key up, and speak into the microphone, we can actually see the amplitude modulation of the carrier. And we can kind of make some measurements of, or at least make sure we're not flat topping, and take a look and see if we're, those little bright spots when I get really loud into the microphone means we're getting pretty darn close to 100% modulation, but we can still see that pretty easily. So now if we take a look at the other channel, there we go, channel 2, this is the RF detector, so if I just key up, we can just see the amplitude just goes up here, okay, and we're in AM mode here. So again, if I go in and talk to the microphone, I literally just doing an amplitude detection of the RF signal. So I can literally see, you know, my modulated tone, you know, kind of, or excuse me, AM demod of my signal. So very easily. So what we can do also is we can actually show both of these together. It's kind of interesting, and we'll literally be able to see both the RF carrier and the demodulated piece of it. So I've got them positioned so that the detector is riding right on top of the RF, so it almost looks like we're just enhancing the top line. So it's just another way of looking at this. So what's also interesting too is that since we have both of these signals, if we have the detector view drive the X input, okay, we're going to go into XY mode, and the Y input being driven by the RF, we could do what's commonly called a trapezoid measurement. So when I'm not keyed up, because there's just a little bright dot on the screen, when I key up, I can see the vertical that's being driven by the RF magnitude, or excuse me, the RF carrier. But then as I speak, the X is being driven by the modulated tone. And people call this a trapezoid pattern. And you can kind of tell if we go all the way down to a point over there on the left, that's kind of indicating to us that we're getting close to 100% modulation. We're completely squelching the carrier. And if we go over to the right, we can kind of see, you know, the maximum amplitude. And you really want to see perfectly straight lines here to show linearity. Something else we can do here, let's go back to kind of our mode here. I'm going to switch the transceiver over to single sideband mode. And if we look at single sideband, we can also look at the RF envelope of the single sideband carrier, or the single sideband signal. Single sideband doesn't have a carrier. We can actually just see the modulated RF output. And this is helpful to look for flat topping and look if you've got noise on your signal. So nice way to kind of monitor what's going on in your RF. So there's a simple little circuit to look at what's going on in your ham radio transceiver RF output. My friend Marty suggested that I do a short little video on using a two-tone test to look at the linearity of a single sideband transmitter. So that's what we're going to do. We're going to do a short little test here with this ICOM 703 QRP transceiver. We're going to generate a couple of test tones with this signal generator here, one at 750 Hertz and another at 1.333 kilohertz. And that means one of the important conditions for this test is that the two tones that are used are not harmonically related. Those two tones are going to be quickly added together in this quick little summer circuit here. The output of that is going into a speaker, and I'm going to couple the microphone to the speaker just to kind of make our measurement pretty simple. And then we're going to sample the RF output through my little RF sampler we looked at in another video. And then we'll take a look at the output on the scope. So let's put the camera down here by the scope, and we'll talk about this test. So when you put a single audio tone into a single sideband transmitter, it basically creates a CW carrier. That carrier is at the suppressed carrier frequency, in this case 7.2 megahertz, either plus or minus the audio tone. So it depends on whether we're looking at upper or lower sideband. In our case, it really doesn't matter. We are testing actually for lower sideband here. So when doing this, you can look at the single tone, single carrier frequency of either one. So if I key the transmitter, I can key the transmitter and talk, and this is kind of what we looked at the other day and being able to see the modulated output, but how do we know if we're linear or not? So let's go and look at this thing with the two-tone test. So if I put the microphone by the speaker, and I turn on the 750 Hertz tone, I can see I've got about 2 divisions of magnitude there, if you will, of the signal. So that's good, and that's kind of our reference point. But you really can't tell whether we're linear or not. Let's look at the other tone. We've also got about 2 divisions of deflection there as well. And that's the other important condition for this test, is that you want both of the two tones to create the same RF amplitude at the output. So you can adjust the signal generator to make that happen. Now what will happen when I turn both of these on, they're going to beat against each other. Basically, they'll periodically constructively add up and destructively add up and create a beat pattern. The beat pattern will have a frequency that's equal to the frequency difference between the two tones. So we turn on one tone and then the other. There's our beat pattern, and that's exactly what you're looking for. You want to see this perfectly linear type of response, meaning that you've got a nice sinusoidal variation. In the envelope, you're crossing right at 0, completely quenching out, and you've got this nice sinusoidal pattern. That's a nice linear transmitter. Now I'll give you an example of what it looks like if we do something to make it nonlinear. Like if I increase the gain of this, the audio signal here. Okay, now there's what it looks like if we're nonlinear. You can actually see some flat topping here. The signals are not beating linearly against each other anymore. We're not completely squelching out at 0. That's your indication that this transmitter is not behaving in a linear fashion. And now we return the gain back to normal, and that's what it looks like when it is operating in a nice linear fashion. So you could also make measurements of the peak-to-peak voltage here, and actually make measurements of power and things like that if you chose to do so. If you calculated power from the peak voltage here, that would actually be what's called the instantaneous peak power. For the two-tone test, winds up being exactly double the peak envelope power that you would normally get if you calculate peak envelope power in a normal way. So, but just a kind of interesting way of kind of being able to go and make these measurements here and looking at linearity. Alright, we're going to take a quick tour of probes and how to use different types of probes, primarily simple passive probes with your oscilloscope, and why you need to use them. So we've got to think about, if we're going to connect up our scope to our circuit, how do we do that? Well, you might just say, well, why don't I just use a simple set of probes like I use with my voltmeter, right? I can kind of put them together in this little adapter here and stick it on the front end of the scope. So let's do that. Let's look at what happens. So you can see the scope trace is kind of all full of noise. It's picking up all the 60 cycle hum from my lab bench here, and all the lights and things like that from the ballast and the fluorescence and all kinds of nasty noise. And that's the problem. If you're trying to look at low-level signals and things like that, connecting up with leads like this is going to present a number of different types of problems. And let's look at why. So it helps to start off by looking at what the scope input looks like. So that's kind of what the oscilloscope input looks like. It's basically almost most of the scopes will have a 1 megohm input impedance, so basically right behind the front panel connector it looks like a 1 megohm resistor to ground. And that's typically got in parallel with it anywhere from 10 to 25 or 30 picofarads of capacitance, sometimes a little more, sometimes a little less. Okay, so it's a pretty high impedance, just like your voltmeter is, but it also has a lot more bandwidth than your voltmeter, so it's going to pick up all kinds of things. So if we just connect up the wires like we just did, this is what happened here. So we connected up these wires. They basically look like big antennas, okay? And so even if we connect it up to a circuit, it's a circuit impedance, you're still going to be injecting noise into your circuit, and you're also going to be injecting noise into your measurement, okay? So it works, as long as your signals are really low frequency, okay, or you've got some really large signals you're dealing with. Otherwise, you're adding a lot of inductance into the measurement path. You're picking up all kinds of stuff with these wires, and they're acting like antennas, and you might even couple some signals to other parts of your circuit. All things that are not really good. So typically why we don't use wires. So another way around that is, well, let's make these wires shielded, use a piece of coax. And if we do that, so now we can wind up with this situation here, and this actually solves some problems, okay? Because now that the signal wire is shielded by ground, we're not going to be picking up a lot of signals, so that's good. We're going to minimize coupling to other parts of the circuit, so that's good, okay? But what's bad about this? Well, it adds a lot of capacitive loading. The way to think about this is that typical coax, the miniature coax you might use, like RG174 or something like that, may have 25 or 30 picofarads of capacitance per foot. And if you're talking 2 or 3 feet of cable, of coax to connect to your circuit, that coupled with the 10, 20 picofarads of capacitance at the input, you could easily add 100 picofarads of capacitance to your circuit by simply connecting the probe. Now, will your circuit care? Depends on your circuit, right? Sometimes it will. You have to remember that 100 picofarads at looks like 50 ohms at 30 megahertz. That's a far cry from the original 1 megohm input impedance that we were dealing with to begin with. So, but this is a basic 1X probe design, and they're out there, and you just got to be careful when you can use them and when you can't. Just take care, and understand the ramifications of touching this probe to your circuit and how it will affect it. Think about would I want to solder in 100 or 120 picofarads of capacitance to my circuit at the point I'm trying to measure. Okay, and expect the circuit to still work. A lot of circuits, will work just fine. Audio circuits, low frequency things, lower impedance circuits, and generally might be okay. But for a large majority of circuits, the amount of loading from a 1X probe is not going to be good. The capacitive loading could really affect the circuit operation. So how do we isolate the capacitive loading of this type of a probe, a 1X probe, from the circuit? Well, one way to do that is to stick a big resistor in series with that. So we stick a 9 megohm resistor in series with the coax. What that's going to do is now all the capacitance is sitting back here is really kind of isolated away from the circuit we're testing over here by this 9 megohm resistor. So your circuit really doesn't see it. So that's good. Okay. Now the resistor, we chose 9 megohms because it gives us a nice convenient 9 megohm to 1 megohm resistor divider here. So it's a 10x resistor divider. Hence that's the reason why we call this a 10x probe. It doesn't have 10x worth of gain. It has 10x worth of attenuation. So it'll attenuate the circuit, but or attenuate the signal by a factor of 10. But that's pretty easily compensated for. But it also reduces the capacitive loading, so that's good. Now the problem that you can run into, though, is that the 9 megohm resistor, okay, and the capacitance of the coax and the scope form an RC low-pass filter that looks like this. Okay, and what happens is as the frequency goes up of what we're looking at here, the capacitive reactance here starts going down, and all of a sudden this, the 10x divide ratio that we had because of this resistor starts getting dominated by the capacitive reactance of that capacitor, and we start rolling the signal off. So it's a low-pass filter. So now as the frequency increases, our 10x attenuation got worse and worse and worse. So it didn't really help us that much. But there's actually, it turns out, a pretty simple fix for this, and this is what's typically done with 10x probes. So if we look over here to the last page here, what we do is add a compensation capacitor in parallel with that 9 megohm resistor. And the idea there now is that for low frequencies, the 10x attenuation is dominated by the 9 megohm and 1 megohm resistor. Okay, so that kind of dominates our 10x attenuation. But now as the frequencies go up, okay, the capacitive reactance of the scope input and the probe cable is going to start dominating the input impedance of the scope. And then so what we do is we add a compensation capacitor here, which kind of will now track that. So now at higher frequencies, if we make the ratio of this capacitance to this one 10x, okay, now that capacitive voltage divider is going to dominate the attenuation at high frequencies. So now between low frequencies and high frequencies, we've got still 10x attenuation. Okay. Of course, the input impedance at high frequencies is going down because this looks like this series combination of capacitors. But at the end of the day, the probe is still flat in frequency response generally. Okay. So we basically can account for that, and this is basically the design of commercial 10x probes. Now they're called 10x probes because they attenuate by a factor of 10. So that's something that's important. You've got to think about that, is that when you connect this probe up to your scope, you've got to remember that the probe is actually attenuating the signal by a factor of 10. Some scopes and probes help you out with that and actually remind you that that's what it's doing, but most of them don't, especially the lower cost ones. So we connect up we'll look at some typical 10x probes here. Let's go take a look at some of these. I'm going to clear out these other probes, DMM probes, out of the way here. And let's look at one. Here's a 10x probe. This is a Tektronix P6105. Okay, it's a 100 megahertz 10x probe, 2 meters long. We'll take a look at, this is the part that would connect up to the scope. This is the part that would connect up to your circuit. There's your ground lead right there. A lot of these have got removable spring clip tips, so you can be probing around with the tip here, or you can connect this up and you get a nice retractable clip, so you can clip this thing into your circuit. Okay, number of different variations on this set of combinations, but this is typical of what you'd find. Now, either on the probe handle itself, like this, or on the compensation box or probe body here, you'll find the compensation adjustment. If we look in this one here, we can actually see there's a little screw with a trimmer cap to set up the compensation for that probe. Here's another example of one here. This is also a Tektronix. This is a P2220. There's our compensation adjustment right there. Okay, and there's our ground lead and our probe to be able to connect up. And we'll look at a couple of other examples too. But one thing I wanted to point out that's different between these two, if you look carefully at the end of these, I don't know if you can see in the camera or not, but there's a little metal pin sticking out of this one. There's not sticking out of this one here, but there's a little metal pin sticking out of the end of the connector here. And what that is, it's something that Tektronix called the Tech Probe interface. And for scopes that were so equipped, when you connected this probe up to the scope had a little sensing ring. In fact, we can look at that over on this scope over here. There's a little sensing ring right around the BNC connector here. And that BNC connector, when that little pin connects to that, that would tell the scope that this is a 10x probe that's being attached, and would adjust the scale appropriately. Okay, most scopes, especially non-Tektronix scope, don't have that little sensing ring around the BNC connectors where you connect the scope up. So when it comes to, you know, making sure that, okay, is my scale correct for the 10x probe, you've got to worry about that yourself. So even if the scope, you know, channel says 50 millivolts per division like it does here, when I connect up a 10x probe, that is now 500 millivolts per division. Okay, it doesn't tell you that, but you've got to think about that. This probe actually has a switch on it, okay, to go from 1x mode, which is just basically a cable connection, you know, or coaxial connection right to the probe tip. That's going to have, you know, 100 picofarad capacitance or more, but it doesn't have the attenuation. And there's a 10x mode to do what we've been talking about. So now the trick is, how do we adjust that compensation capacitor, okay, to make sure that we match the input capacitance of the scope? Because some of them are quite different. This scope here, that input capacitance might be hard to see, says 25 picofarads. This scope over here, that one says 1 megohm and 15 picofarads. So that's quite a difference. And they certainly, a scope that's matched to this scope here wouldn't necessarily match to this other scope over here on the right. So that's why that compensation capacitor is made adjustable. So how do we adjust that? Basically, we use a little test signal, or calibrator signal, a compensation signal, and it's typically a square wave. The square waves are nice because you can have a fairly low frequency square wave that has very fast rising and falling edges, and what that gives you is a waveform that has a lot of low frequency components and high frequency components, because basically a square wave is fundamental, you know, frequency of the square wave is energy, but then you've also got energy at all the odd harmonics at 3 times that frequency and 5 times and 7 times, etc. The more high order harmonics that you have, the faster the rising and falling edges. So it's a nice waveform that has both, you know, fast, or I should say high frequency energy and low frequency energy in it at the same time. And the way to adjust these probes is actually quite simple. Let's kind of look at the example over here on this scope. Okay. So in this scope here, I've got, this is a P6131 10x probe connected up to channel 1. And on this scope over here is our calibrator signal. Okay, and I've got the ground lead already connected. If we connect up the scope to it, the probe to it, and we could take a look here at the on the waveform. And this one is pretty well compensated. Now you may notice when you get a 10x probe, they'll always come with, when they're new, a little diddle stick, a little screwdriver. This one actually still says Tektronix on it, but it's just basically it's a little non-metallic screwdriver to adjust the compensation capacitor inside the probe. Like I said, sometimes those compensation adjustments will be on the probe body, and sometimes they'll be right on the the probe box that connects up to the scope. And this is the waveform that we're looking at here is typically what you'd ideally want to see, in that it looks like a perfect square wave. And here's what it looks like if you have it misadjusted. Let's see if I can engage the screwdriver in here. There we go. And you can see if I make that capacitor too big, okay, we're going to couple more high frequency energy in, and we're going to get this overshoot on the rising and falling edges of the square wave. And if we adjust it the other way, where that capacitor is too small, now we're low pass filtering that square wave, and we get this kind of rolled off response there. So the idea is to adjust this thing. If we kind of go back and forth, we can adjust that until we get a really nice looking square wave. And what we've done now is made sure that the low frequency response which is kind of set up by the resistor, is now matched by the high frequency response set up by the capacitive voltage divider of the 9 mega ohm resistor and the parallel capacitance, and then the cable and input scope capacitance. And now this probe will be good for looking at both high frequencies and low frequencies. But you'll notice again, this probe, if we look at the scope, you might see that the scale on the scope says 100 millivolts a division. If I remove this scope, this probe, you can see that drops to 10 millivolts a division. This probe has got that little metal pin, and this scope is automatically sensing that. There are other scopes that sometimes will actually have a little light that will tell you whether you've got 1x or a 10x attenuation, on some of the Tektronix scopes. But the non-Tektronix scopes typically don't have that sensing ring, or at least most of them don't. So if you put a 10x probe on there, you know you've got to multiply your volts per division setting by a factor of 10 when you're using the 10x probe in order to make a calibrated amplitude reading. So that's a quick tutorial on what 10x probes are and how to adjust them. Make sure that they're calibrated for anytime you change a scope, and you can use the same probe on a new scope, readjust that for that new scope, because no two scopes really match in terms of their input impedance, and properly adjusted probe on one scope won't necessarily be properly adjusted for another scope. Okay, this video is going to talk a little bit about the triggering controls on an analog scope. So triggering is used to synchronize the sweep of the beam across the screen to the signal that you're looking at. And triggering controls are usually all kind of grouped together, like they are here on this 465B Tektronix scope. We're going to talk about each of these controls. Way to think about it, I'll throw this thing into kind of a slow sweep and kind of a single sweep mode. And the trigger basically says, I'm going to kick off the sweep now. Okay, and I'm just doing a quick little single sweep on this to kind of show that I'm just kicking off the sweep at a certain point in time. Triggering is normally done by looking at a portion of the input signal and telling the sweep to go across at the same point in time in a repetitive signal or any kind of a signal. So we're going to talk about kind of how that works and the controls that we have. So I just have a sine wave going into the input here. I'm DC coupled. You can kind of see the DC coupling control here, and we're just looking at the waveform. And you notice the waveform is starting at one particular spot. Okay, so looking at the trigger controls, we'll see what kind of controls that. So down at the trigger controls, we've got a couple of things we can look at here. We have a level control, okay, which is right here. Level and slope, we'll talk about what that is. There's also a source control. If you kind of look above there, it says source, and coupling, and trigger mode. We'll cover each of these things briefly. So what we're doing is the source control says, what are we going to trigger on? What signal are we going to use as our synchronizing reference to the signal we want to go look at? So on most scopes, you'll at least have the ability to trigger on any of the channels that you're looking at. Like you can see here, so I've got channel 1, channel 2. I've got so I can literally trigger on the signal coming into channel 1 of the scope or signal coming into channel 2 of the scope. If you have a norm position or vertical mode, what that says is that whatever you've got set up for the vertical input, if you're chopping between channel 1 and channel 2 or alternating back and forth between 1 and channel 2, then the norm position or the vertical mode position will trigger on whichever signal is active at that point in the chop or the alternate sweep. So in this case, we've got a signal going into channel 1, so we can either use the norm position or the channel 1 position, like right there. If I go to channel 2, we can see I don't have a synchronized sweep here anymore. I don't have a signal coming into channel 2, so the sweep is kind of unrecognizable. If I bring this back up to channel 1, boom, we're triggered again. Okay. We also can trigger on line. What line means is it basically looks at the 60 hertz line, 60 hertz here in the US, and triggering on the line current, so every 16.7 milliseconds. There's also an external trigger on this scope here, which allows me to couple into a signal, or couple another signal into here and trigger on that and view my channels 1 and 2 with respect to some external signal. Okay, so we'll leave it on channel 1. The mode and slope control here says where am I going to trigger on the waveform. Okay, so the level control is a control that I can move back and forth kind of vernier here. Okay, and if we look at this, if I'm moving this positive and negative, let's look at what happens on the scope at the same time. If you look very carefully at the leading edge here, if I move the trigger level up, we can see we're starting the sweep at a later point in time, or a higher point in the voltage. If I move the trigger level down, we're triggering at a lower level in the voltage. So you can pick and choose where in the waveform you actually want to trigger. So if you get a more complex waveform than I have right here, you might pick a particular amplitude or something to go trigger on. So very common if you have some distorted waveforms, you might try to adjust the level so that you only pick off the peak of the signal instead of somewhere in the middle, so you don't get kind of a double or triple waveform kind of on the screen. Now the slope control is this little switch here in the middle. Okay, positive or negative says that do I want to trigger on when the signal is coming up through that voltage, or when it's going down. If I switch it to negative, now I can trigger on when it's going down through that threshold. So the level that I've set, do I want to trigger when my signal crosses it from coming from above, or crosses it coming from the bottom. So that's a positive slope trigger and the negative slope trigger. So that's what those two do. So if we see if I adjust that, we can actually see that change. Okay, so that's what the level and slope and the source controls do. Now the coupling control, this one's kind of interesting. The coupling control basically says, okay, I know I'm going to trigger, say, on this source, but how am I going to take that signal and couple it to the trigger circuit? Okay, if I go to simply DC coupling, okay, which is what I've got right here, let me adjust my level here again. Okay, what that says is I've got whatever I've got coming in here, I'm DC coupling that into the scope. I can adjust my slope up or down, okay, and trigger on that. But if I adjust the DC offset on my signal itself, okay, watch what happens. You can see the signal is moving, the whole signal is moving up or down, okay? Now if I move it outside of where my trigger level is set right to the middle of the screen now, and if I move the signal past that, I'm not triggered anymore, okay? Because my trigger level is kind of fixed in the middle of the screen. If I move this up here and now move my trigger level up higher, I can actually trigger on that signal again. Now I can see my trigger level is sitting right up right there. And if I move my DC level of my signal again, now I'm going to move around that. Okay, so that may or may not be convenient for what you want to do. You may actually want to try and trigger on this signal regardless of where it is sitting, DC wise. So the other very common trigger coupling control to use, instead of using DC coupling like we're using right here, is to use AC coupling. If I move that up to AC coupling, okay, and now if I set a threshold like in the middle of that AC signal, regardless of its DC offset, I'm still triggering on it because the AC coupling is removing the DC component of this signal, and I'm only triggering on the AC component. And typically that cutoff frequency is somewhere around 20 or 30 hertz. So anything that's above 20 or 30 hertz will get coupled to the trigger circuit, and anything lower than that essentially gets rejected or blocked by essentially the AC coupling. So that's kind of a very common control to use. It makes it really easy to trigger on signals regardless of what their DC offset is, if we kind of adjust that up or down. Okay. There's other two, some scopes have these, some do not. You'll see one that says LF reject and HF reject. That stands for low frequency reject and high frequency reject. And what that low frequency reject is basically another form of AC coupling, but with a higher frequency high pass corner. Where AC coupling, anything above 20 or 30 hertz will essentially go to the trigger circuit. The low frequency reject moves that high pass corner to probably something more like 50 kilohertz or more. Again, it's going to vary by scope, but that means that anything below 50 kilohertz now is rejected. So all the audio frequencies and things like that are blocked. So only very higher, much higher frequencies, higher than audio frequencies, ultrasonic and higher, are going to get coupled to the trigger circuit. HF reject is kind of in between the two. So what HF reject does is rejects everything, say, above that 50 kilohertz. Okay, so all the high frequency, radio frequency, high frequency stuff will be rejected. So everything above 50 kilohertz will not get coupled to the trigger circuit. It's also still an AC coupled mode, so you're still going to block everything below about 20 or 30 hertz. So it's really kind of a bandpass coupling for kind of audio frequencies typically, but again, it'll vary by the particular scope and manufacturer that you're dealing with. Not used that often, but they are there, and they can come in handy for some complex waveforms sometimes. Now, on some other scopes, you also see coupling that are for specific to old analog television signals, like NTSC signals, and you'll see something that says like TV horizontal and TV vertical, and that's designed to trigger on a portion of the NTSC composite video signal, the horizontal blanking, or the horizontal retrace, or horizontal sync pulse, and the vertical sync pulses that are in those waveforms. But if you're not working on TVs, you probably don't have to worry about those. Now, the other important controls for triggering are the mode controls. And you'll see I've got here, it's got 3 modes. We've got auto, norm, and single. And what these are basically going to control how the trigger circuit's going to work. If you have an auto control, I'd recommend using that, because what that does is, in the absence of a trigger, if you don't have the trigger circuit set up right, let's say for example I move this threshold or the level way out of whack here, okay, and you can see I'm not triggering, but I still have a signal here on the scope. I still have a trace, because what the auto mode does is that if I don't get a valid trigger based on what I've got set up here, it sends a sweep anyway about 20 or 30 times a second. Okay, it'll re-trigger the circuit automatically. So it's helpful because it'll at least put something on the screen so you've got something to look at. And that's what the automatic trigger mode does. If we switch to the normal trigger, you can see now I don't have a trace on the screen because I had messed around with my trigger level control. And now I'll have to kind of play with the trigger level until my signal comes back. And we can see the signal only comes up when I've got the trigger level kind of sitting within the signal boundaries. Okay, so that that's useful, but if you're dealing with very low repetition signals where the signal doesn't repeat itself anything more than 20 or 30 times a second, you probably have to use the normal. Otherwise, the auto trigger will send a sweep when you don't want it. But normally, you can use the auto trigger mode. That way, you'll always have a trace whether or not you got the trigger set up right away. And Tech kind of adopted the policy that if you set the threshold to kind of mid-scale, or the level to mid-scale, and you push all the other controls to their top positions, auto, AC coupling, normal, you'll almost always have a trace. So it's a good starting point. And some other scope manufacturers have kind of adopted that as well, that turn all the switches up, and it kind of gives you in a mode where at least you'll get a trace and you can start from there. Now, there's one other control which a lot of people maybe don't really know a lot about, is this one down here called hold off. Now, what the hold off does is it kind of controls how quickly the scope will re-trigger or rearm the trigger circuit to get ready for the next sweep. Normally, it's set all the way to kind of its minimum position by turning it all the way down. Okay, and what that says is that once I send a sweep across the screen, as soon as it's done, I get ready to sweep again and rearm the trigger circuit, wait for the next trigger to go again. Now, in some cases, you might have a complex waveform, or maybe if you're looking at digital signals and you're looking at like a series of pulses, and then there's going to be a gap, and then another series of pulses. Sometimes you don't want to trigger right away, because maybe when it comes right back and is ready to sweep again, you're going to be in the middle of the next repetition of waveforms. And let me show you an example of what that might look like. I'm going to create a bursted set of signals here. Okay, out of my signal generator. So now I've got a bursted set of sine wave, if you will, and then it goes quiet for a while, and then it comes back on. And you can see it looks like they're overlapped here, because what's happening is I'm getting one sweep, okay, and then it's kind of going quiet, and then when it gets ready to arm again, it comes up somewhere in the middle of the next burst. So I get these signals that kind of overlap. fact, I could see this if I go to kind of my single sweep mode and I push the single sweep button. I can see that with the repetitions, I don't really have an overlap. I just have kind of one version of the signal going here. So if I go back to my triggered mode, what the hold off allows me to do is to adjust the amount of time that the trigger circuit's not going to look for another trigger. So if we adjust this control, we can slowly move this thing up and eventually reach a point where we've told the trigger to hold off long enough so that when it rearms again, it's ready right at the beginning of the next sweep. And there we go. So now I've got a nice waveform. I just adjusted that hold off control, and it's just something you play with manually and watch the screen. So now I've actually adjusted it so that I'm triggering at the first cycle of my burst here, and I'm getting the burst, I'm getting the quiet time, and the part of the next burst. But now I've told it, hold off the trigger for a certain period of time that I've adjusted here, so that as soon as it rearmed again, it was ready to kind of see the next burst coming across here. And if you don't have that adjusted right, you can get kind of this overlapping kind of waveform, and once you get it adjusted right, you can kind of stabilize these more complex waveforms. So it makes it easy to really kind of trigger on these complex, periodic, bursty type of things that would be very tough to stabilize and get without that kind of control and looking at it this way. So anyways, that's kind of the basic controls that you would have on a typical triggered sweep oscilloscope, and how you would use and adjust each of those to get a nice stable display. I hope this has been helpful. Okay, with this video, what we're going to do is take a look at how you can identify or characterize the key-up characteristics of a radio transmitter. And the examples we'll use here are a couple of handheld amateur radio transceivers. This first one is a Yaesu FT470, and it's a dual band radio that's probably, I don't know, 20 plus years old, 2 meters and 440. And the other one here is a Kenwood. This is a tri-band handheld transceiver, 2 meters, 440, and 220. And we'll take a look at what these transmitters do during key-up, how they behave. And you'll see that even though they're both amateur radio transmitters, they both behave quite differently upon key-up. And these kinds of measurements can be used to really help you identify a transmitter, in a crowd of transmitters type of thing. So what we're going to use is this real-time spectrum analyzer here from Tektronix, and how we're going to sense the output of these rigs is this little kind of setup I've got here. Let me kind of pull this up into view. So basically what I've got is just a old BNC cable going into that will connect up to the transmitter, and that's going into this guy, which is just a little RF sampling tee. So it's just a through coax here to this 5 watt 50 ohm termination here. And then this is just a variable sampling tee. We can kind of just pull this in or out to kind of adjust, how much coupling we get. And then that's going into the input of the spectrum analyzer over here. So we're not going to transmit out over the air. It's going to transmit into the dummy load, and then be able to characterize what the transmitter is doing. So I just hook the coax up to this transmitter. We'll turn it on. And if we look carefully here, we can kind of see that it's at 146.55 megahertz. That's going to be our test frequency for this particular set of measurements. Now let's take a look at this on the spectrum analyzer. So let's just kind of zoom in a little bit on that. And we'll kind of zoom in on the display here. Okay. And so in doing such here, let's see. What I'll do is key up the transmitter, and we'll see a couple things. I can see my voice being picked up by the transmitter, and we can actually see as an FM transmitter. You can actually see the modulation here. But what's also interesting is what we really want to do, though, is characterize what this thing's doing during key-up primarily, because that's kind of a good way of identifying, maybe what a transmitter looks like. So I'm going to not say anything and key this transmitter a couple times and watch the spectrum. What we're looking at, by the way, is a composite spectrum that's composed of making about 300,000 spectrum measurements per second, and then showing all the results on a display, color coding essentially the density, how often each area is occupied. So if I unkey, and I'll just key this thing a couple of times and take a look at the display, and we'll kind of look at what we're seeing. You notice as I key and unkey that we're occupying a whole bunch of spectrum. So I've got this thing, we're looking at a 20 kilohertz span here. I'm going to take the span and bump it up to about 100 kilohertz. So in doing that, it's a little tougher to see, the modulation, but let's do the key and unkeying here again. So we kind of see that we're occupying a fair amount of spectrum. I mean, nearly 100 kilohertz or more, during key up and key down. So let's go characterize what that's doing. With this analyzer, we can actually capture some of that over time. So let's go add a couple of displays here and take a look at what we can see. Let's bring a couple of displays up here. Okay, so what I'll do is I'm going to set this up to, I've got this set up to capture data when I key up, so let's just watch it. Okay, so in doing that I can see a couple of things here. I've got a couple of displays. Let's look at this display down here. This one we call a spectrogram. And this one allows you to look at the spectrum and how it varies over time. In fact, what we'll do is let's kind of make that bigger. And I'll zoom in on this a little bit. Okay. And what we can see is that when this thing keys up, that the signal kind of comes up from high frequency and then kind of goes low, comes back high, goes low, and ultimately settles back out again. Okay, and we kind of compress this back out, we can actually see that. So I can actually see the key up characteristic here, that the spectrum actually wiggles around quite a bit before it finally settles out. In fact, we can make a quick measurement of how long that takes. If we say key up is happening right about there, move another marker here and say we're settled out right about here, and the time distance there is about 25 milliseconds. So the first 25 milliseconds of that key up, okay, is kind of this wiggly type of thing. Okay, it's kind of interesting. We could also bring up a display called a frequency versus time, which is kind of an FMD mod. Okay, and if we take a look at that characteristic, that's this display right here. So here now this vertical axis is frequency deviation. The middle of it is right at, essentially our center frequency of 146.55. And I've got plus or minus 5 kilohertz. So each division here is about a kilohertz. And then the horizontal axis here is time. Okay. And we zoom in on this, we can actually see at this, right at the beginning here, we can actually see that wiggling characteristic that we were looking at earlier. Okay. And in fact, we'll just kind of bring this back up here as well on the spectrogram. Okay, so let's bring that right back into view here. There we go. And if I move that marker through here, I can actually see how the spectrum is changing over time, how the frequency deviation is changing over time. So this is kind of a unique characteristic. So if you were able to catch, if somebody was doing something, or using a transmitter, you wanted to try to identify it, if you could capture it off the air, you'd literally be able to see this characteristic and say, hey, that's that transmitter. So so let's go look at the other transmitter I have here and see what we can see with that one. So I'm going to change some of these scales back for us, and then we'll go back and look at that. Okay. So I'm going to switch over to the other transmitter that I have here. Let's go bring that up on the big DPX display. So I'm going to switch over to my Kenwood, turn it on. There we go, and hook the transmitter up to it. And if we look at this one here, this one is also sitting at 146.55 megahertz. So if I can get you a picture of that without the glare, I don't know if I'll do that or not. Here we go. Okay. So now when I key this one up, let's look at what it looks like. And let's see, we got to tell this thing to run. There we go. So now I can see this one. I can see myself talking. Let's just kind of key up and key down a couple times and see what we can see. Well, certainly this one looks a little bit better behaved. It's not occupying nearly the 100 kilohertz of bandwidth that the other one was. So what we can do is we can cut our span down here. Let's go down to about 20 kilohertz. So now I can actually see, there's my voice modulation again. And now let's look at what this one is doing with key up. So interesting. I'm doing this a couple of times, so maybe you can see what I'm seeing. I can see a couple things. If you look carefully, there's two things that I'm looking at. One is you can see that the carrier, when it comes up about 1.5 to 2 kilohertz low, and then scoots up to this center frequency fairly quickly. But also less quickly, you'll see a couple of sidebands right about here where I've got the mouse, and then right about over here where I've got the mouse, that take almost a half a second to completely die down. Couple low, very low level modulation sidebands. So I'll be quiet again here while I key up and down and take a look at that. So watch the center frequency, how it scoots over. But then also see those sidebands right about over here, and the same on the other side. So that's real time. I was just literally being able to see those things kind of die away in time here. So let's look at that with the same kind of displays we were looking at earlier. Okay, so I'm going to key up and we'll just watch this thing. So kind of interesting. We can let's kind of zoom through this display. So things look a little bit cleaner here. Okay, we're not getting nearly as much of you know, the same type of disturbance and wackiness that we're getting at key up with the other one. So let's go actually take a look at it. We'll do a quick little quiet key up and go look at it. All right. So now if we look at, say, that spectrogram that we were looking at earlier, which is kind of looking at how the spectrums change over time. If I grab this marker, we can actually see this. You know, actually I'm going to close this display to make this guy big. Let me pan this down a little bit so I can kind of see better. So now if I kind of look at right at the key up characteristic, it comes up slightly. You know, right here at this point in time, right after key up, I'm sitting about 1.6, 1.7, 1.8 kilohertz low in frequency, and the thing kind of scoots over time, and finally settles out about you know, carrier center frequency right about there. So it takes, let's say in this case, let's kind of look at this, about 80 milliseconds or so to kind of settle out to, you know, within a few hundred hertz of you know, of final frequency. But it's taken even quite a bit longer. If you look at these little sidebands over here, it takes quite a bit longer for those things to kind of go and die away. I get all the way down to here where they're finally in the noise right about way down here, and that's a little over 400 milliseconds later. So there's those little kind of modulation sidebands here that we can kind of see that are sitting way out over there. In fact, what I'm going to do is I'm going to put a marker on this so I can let's go tell that marker to be on my spectrogram tray so I can actually see where those things are. And if I pull that marker over here, so there's that marker. He's sitting about 2 kilohertz off frequency, so off of center. Actually, let's do this. Let me take my reference marker as well, put that over here. That's what we want to do. So now I can see this marker here is sitting about 5 kilohertz off of center. This one's sitting about 5 kilohertz on the other side. So I've got some kind of 5 kilohertz modulation, like a ping, if you will, that's kind of dying away as this thing keys up here. So pretty interesting. If we look at that other display we looked at before, the frequency versus time characteristic, okay, and with this one we can see it's kind of a clearer type of a thing going on here. I can literally see that you know, the transmitter is not going through these wild oscillations, if you will, when this keys up. We just got this kind of smooth characteristic right here. You know, about, you know, it comes down, let's see, kind of move this marker down into the trough here. We're down around 1.8 kilohertz, and it very smoothly and cleanly goes up to center frequency. So kind of interesting that we can characterize you know, these two amateur radio transceivers, you know, this little Kenwood THF6A and this older Yaesu FT470, both designed for the same purpose, but both behave quite differently upon key up, with some unique characteristics that could be used to identify them if you ever needed to. So anyway, that's a quick little view of what you could do with a real-time spectrum analyzer to characterize the transient characteristic of transmitting devices. Okay, in this video, just a quick thing to compare kind of the spectrum analyzer performance of this new Tektronix M0ODZ mixed domain oscilloscope with kind of an entry-level spectrum analyzer. The spectrum analyzer portion of the MDO is designed to essentially be a replacement for kind of entry-level benchtop spectrum analyzers, and this Agilent ESA E4411 is kind of a typical entry-level spec amp. So we're going to compare these two. So let's set up just a spectrum analyzer only on the MDO here, and let's just set a couple of basic settings. Like I'll set center frequency to about say 300 megahertz, maybe a span of say 100 megahertz to go play with here, and let's set a resolution bandwidth of 300 kilohertz. Okay, so let's set the same thing. And also let's set the reference level here to let's say minus 30 dBm. That'll ensure that kind of the attenuators are all off and we're looking at the raw noise floor of the instrument. Okay, let's go set the same thing up on the spectrum analyzer up here. So we'll set let's see, center frequency 300 megahertz, a span 100 megahertz, resolution bandwidth of 300 kilohertz. Oops. 300 kilohertz, and reference level of minus 30. Okay, and if we take a look at this, we're sitting, noise floor sitting at about minus 85 or so, and minus 85 dBm. Say there's a minus 30 dBm reference level, attenuator is at 0, center frequency is 300 megahertz, and span of 100 meg. Let's look down here on the MDO. Okay, we're sitting at reference level minus 30, and center frequency 300, span of 300 kilohertz RBW, and we're sitting noise floor wise somewhere between about minus 100, minus 105. So about 10-15 dB better here, which is nice. Okay, of course it's a newer instrument. So what's really interesting is we start comparing the sweep speed that we're getting on a conventional swept analyzer versus what we get in terms of a waveform update rate on a discrete Fourier transform based analyzer like the MDO. The MDO, because it does Fourier transforms, it really is capturing data over time, sampling up just like an oscilloscope does, but then applying that sampled data to a discrete Fourier transform to give you the result. So there's no sweep per se, but we'll be able to compare waveform update rate to sweep speed. So if we look here, we're looking at a res bandwidth in this case of 300 kilohertz. Okay, and a sweep speed, we could see there's 5 milliseconds. Okay, and you can kind of see how lively the display is, how quickly it's updating there compared to what we've got down here. And I would say they're simpler. I mean, no one's going to complain about either one of them. Let's start taking the res bandwidth down here, and so let's go from say 300K to 100K. Now at 100K, the sweep speed goes to 25 milliseconds. And if we come over here and set the res bandwidth from 300 kilohertz, and let's set it to 100 kilohertz. Okay, kind of tough to see, really no real change in the waveform update rate. You can just kind of watch how lively that is compared to the display up here, and I'd say we're still comparable, we're still about the same. Let's cut it down again. Okay, let's cut the res bandwidth, say from, let's see, at 100K, let's go down to 30 kilohertz. And let's set the same thing, 30 kilohertz here. So with 30 kilohertz RBW, we can start to see the sweep speed slow up here. You can actually see the sweep going across. And we can actually see that the sweep speed is actually 277.8 milliseconds, okay? Or about a little more than a quarter of a second per sweep. So we're getting almost 4 sweeps per second. If we look at the waveform update rate down here, to my eye it looks like it's probably a little faster than 4 per second, but so I think we're starting to get to the point where this analyzer is a bit faster. Again, compare the sweep speed here, and kind of just watch the waveform, how fast it's updating, compared to what we've got down here. Let's start cutting the RBW even more. Instead of say a 30 kilohertz RBW, let's go to 10K. That's the next step size on my swept analyzer above. So let's set 10 kilohertz up here. Let's set a 10 kilohertz RBW up here on the Agilent analyzer. So now in this swept analyzer, you can actually literally watch the sweep. Okay. If we look down here carefully, we can see the sweep speed is 2.5 seconds. Okay. So it takes 2.5 seconds to do one sweep, across the whole span there of 100 megahertz. We compare that to what we've got down here on the MDO. We can see that we're getting a couple of updates per second. And maybe if we're careful and look at the clock down here in the corner, we get them both on screen, you might be able to see we get maybe 4 or 5, maybe 4 sweeps or 4 spectrum updates per second. So we're running about 4 spectrums per second here versus, well, about 2.5 seconds per sweep up here. So we're starting to get some considerably faster. And that's at a 10K resolution bandwidth. The next step down on my swept analyzer is 3 kilohertz. So let's set a 3 kilohertz RBW here. And let's set a 3 kilohertz RBW here. Okay, now with a 3 kilohertz resolution bandwidth, you can actually see the sweep speed, not very fast. Okay, and if we look down here at the sweep speed, it's about 27 seconds, or nearly 30 seconds to do one sweep at a 3K resolution bandwidth. If we look down here, we can see we're getting a spectrum update about once per second. Okay, if we again watch the clock down here, the little tick on the bottom, we can see we're probably getting just a little bit better than once per second. So we're about 30 times faster. So the next stop we'll do, and we'll go any further than this, is let's look at a 1K resolution bandwidth. Let's set the 1K resolution bandwidth here. So now at a 1K RBW, you can see the sweep speed is quite slow. You can see it's starting to work its way across there from the left edge there. And if we take a look at this, the sweep speed is 250 seconds. So it's going to take 250 seconds, okay, to sweep. That's about 3-4 minutes, all right, a couple of minutes that it would take to sweep across here. Let's look at what we've got going on down here. Okay, again, we're sitting at the same setting, 1 kilohertz resolution bandwidth. And if we look at the trace and the clock at the same time, let's see, it looks to me like, about every 2.5 to 3 seconds we're getting an update. So we're talking probably, 2.5 or 3 seconds versus 250 seconds. That to me sounds like about 100 times faster. So this really allows you to use much narrower resolution bandwidths than you would even think of using with your conventional analyzer. Okay, like I'm going to take this marker and move it over here. Let's see where the noise floor is. I move the marker down here so I can easily read about minus 104 dBm in terms of the displayed average noise level here at this particular set of settings, again with a 0 attenuator. So get minus 30 dBm reference level here, so we're kind of apples to apples in terms of what we're looking at here. And I can see I'm sitting down, instead of about minus 104, we're sitting down about minus 116, minus 117. So again, 10 to 15 dB or so lower noise floor. So even though we're saying that this spectrum analyzer that is in this new mixed domain oscilloscope is kind of an entry-level spec an, its performance is actually quite good compared to kind of very popular entry-level spec an in this like the Agilent ESA I've got up here. So really fun. I'm really glad to have one here to play with, and glad to share some of this performance with you. Okay, this video is just going to take a quick look at using a pan adapter on an HF radio to kind of see what activity is going on in the band. So welcome to my ham shack here. Now, we could have focused on this station monitor here, this Kenwood SM220. It has a band scope feature built into it, and is designed to work with a couple of the IF outputs of some of the Kenwood rigs, like this TS830 down here, as well as my TS870. Both of them feature, one of the IFs is at 8.83 megahertz, and so essentially the band scope that is built into this Kenwood station monitor is essentially an 8.8 megahertz, kind of dedicated spectrum analyzer. But we're lucky enough to have here in the shack a new spectrum analyzer. It's actually part of this Tektronix mixed domain oscilloscope. Spectrum analyzer is right here. This one happens to go all the way up to 6 gigahertz, but all we really need to do is look at the 8.83 megahertz IF output of this receiver, and that's what I've got going on here on the screen. So take a look down here. We're let's see, center frequency of 8.83 megahertz. I'm looking at a 500 kilohertz span. I'm using a 3K resolution bandwidth because that's typically the channel bandwidth, or the bandwidth of some single sideband phone transmissions that we'll find on the HF radio. So as you can see, I'm kind of tuned to the 75 meter band. There's some activity going on right here at 3850, and right here in the center of the screen. In fact, let's throw some marker on here. Right, that center marker there is right at 8.83 megahertz, so I can actually see the signal kind of popping up, right here. And what we can see with these other peaks is we're looking at a 500 megahertz, or excuse me, a 500 kilohertz span around 8.83 megahertz. So we're essentially seeing what the receiver sees, plus or minus 250 kilohertz around what we're actually listening to. And if you watch carefully, I'll take and I'm going to start tuning the receiver, up and down. And as I do, you can watch these peaks kind of move across the screen. You see them moving. In this case, they're kind of moving off to the left as I tune the receiver down. And so we can actually kind of tune, and if we kind of look at a strong signal, see that strong signal's coming up towards the center. When I get him in at the center, then I can actually see that I've actually got a strong signal here. Looking at the S meter, I can actually see that pretty strong signal sitting at 3842. I can actually see that in the receiver. I can see there's another set of strong signals just up here, and if we tune over to those, I can tune the receiver over and pick up that next strong one right here. So there's that guy is sitting right here at 3892. So really handy to kind of look at where there's activity on the band so you can tune around and go listen to it. What's also kind of neat, this analyzer also features something called a spectrogram. There's hams in the watching audience who will recognize this as a waterfall display. And kind of same kind of a thing you'd get with looking at a like a PSK31 display. So I can get enough contrast in here and kind of see basically it's just building up, kind of those spectrums here over time. Each of the spectrums, when you're finished looking at it, kind of gets put up into this display, and the color is amplitude. And if I tune kind of sideways a little bit, you'll see those signals kind of move. You can kind of see how they're diagonally moving. Okay, because I've kind of tuned the thing back and forth. So this gives you a way of looking at kind of long-term, receive history in the receiver. But this kind of shows a neat use of using a spectrum analyzer on an HF radio that happens to have an IF output. And I know a lot of the Kenwood rigs, like the 530, the 830, kind of similar to the rig down there in the bottom. I use this also on a 690 and a 450 and this 870. That's also got an 8.83 megahertz IF out. So kind of a neat use of using the analyzer. Right, this video is going to take a look at the difficulties in trying to measure two signals that are at dramatically different frequencies at the same time. And it really comes down to playing a game of sample rate and record length in the scope. So on the signal generator right here, I've got two channels. One channel is putting out a signal at 1.5 kilohertz, and the other one is at 15 megahertz. Okay, so they're coming out here on channel 1 and channel 2 respectively, and bring them over here into the scope. So right now, if we're looking here at channel 1, this is the 1.5 gigahertz or 1.5 kilohertz signal. Look down here at a frequency measurement, I can see it's 1.5 kilohertz. And there's the signal on the scope screen, no problem. So if we kind of switch this over and put the 15 megahertz signal up on the screen here and kind of speed this thing up here a little bit, I can see that this guy is indeed 15 megahertz. Okay, so let's see what happens when we try to look at both of these at the same time. So I'll put the 15 megahertz signal on channel 2, the 1.5 kilohertz signal on channel 1. Let's bring this back down here. So there's my 1.5 kilohertz signal again. I look at its measurement down here. Everything looks good. 1.5 kilohertz. Let's turn on channel 2. Okay. Well, doing that, I really can't see much on channel 2, right? So, what's going on there? Well, one of the things that we can see by looking at this is that we're running at just 10 megasamples per second, right? Because we're running at a very low sweep speed, effectively, or time scale, 100 microseconds per division, and at a 10,000 point record length, which is our default here, that translates to 10 megasamples per second. Well, 10 megasamples per second is undersampling this 15 megahertz signal. So I'm not going to get an accurate representation of that. And we can actually see that if we actually turn a measurement on here for that channel. Let's turn a frequency measurement on for channel 2. And we can actually see the frequency measurement is showing something, it's bouncing all over the place. It's like 5 megahertz, sometimes it's changing. Well, part of that problem is we're undersampling that signal. We're aliasing it. Okay, and if we kind of play around with sweep speed, we can actually see that signal doing all kinds of wacky things. That blue signal is the one that is actually 15 megahertz. and we're undersampling it here by playing around with the sweep speed. So it actually can look like a very, very low frequency signal here, but that's just because we're undersampling it. It's the same effect that makes wagon wheels go backwards in the old Western movies, because you've got this undersampled frame rate, if you will, undersampled sample rate. Or if we speed things up and do a single shot, I can very easily see that 15 megahertz signal, and there it is. But if I speed things up to see that, now I can't see the 1.5 kilohertz signal because it's running, it's too slow. I can't see even one cycle of it. If I slow things down so I can see, a cycle of that, I can't see anything on the 15 megahertz signal anymore. And it really comes down to what's going on with sample rate. Because as I bring the sweep speed up, or the time per division up, I get to the point where I can actually see, my high frequency signal. But that's because now, in this case, I'm running at 100 nanoseconds per division at 10,000 points. That gives me 5 gigasample per second that I'm running here. Okay, but now it isn't helping me in terms of looking at the lower frequency signal. So how do we get around that? The way we get around that is, let's adjust things for our low frequency signal. Okay, but now we're undersampling the high frequency signal, so we need to bring the sample rate up. Now the way that we do that is we're not going to change the horizontal time base, or the time per division on the horizontal scale. We're going to leave it at 100 microseconds per division. But now I want to do more sample points, so what I'm going to do is acquire more data. So instead of doing 10,000 points here, we'll adjust the record length to be something greater than 10,000 points. Let's bring it down to say, or up to say 1,000,000 points. Now if we do 1,000,000 points, now at 100 microseconds per division, 1,000,000 points gives me 1 gigasample per second. That's going to sufficiently oversample this 15 megahertz signal that I've got here, so I can accurately see it. So even though I've got a 1,000,000 points going across the screen here, okay, obviously the screen isn't showing all of them, but the scope is actually measuring on all of them. And this is something that's unique about, or not unique, but I should say there are scopes on the market that even when you set the record length to be very long, like we have here, 1,000,000 sample points, and some of the scopes will only make the measurements on the 1,000 or so points that are displayed on the screen. This scope doesn't do that. This one will make the measurements on the actual sample points, even if it's not showing all of them. In fact, if we do a single shot on this, I can see I've got an accurate measurement on frequency on both of these. And if I zoom in, okay, I'm just going to zoom way in on this. Okay, now I can actually see each of these measurements. So there's my high frequency one. I'm just kind of moving that back and forth. I can see my low frequency signal moving back and forth as I scroll back and forth through this record. Okay, we can actually see me walking through here, so you can actually see each of those signals at the same time. So the key here was to ensure that we captured both of these signals accurately by setting the record length long enough so that the resulting sample rate is high enough to oversample each of the signals sufficiently. And that's really the trick. That's all you have to do. Hey, yesterday I put together a video that showed how to use a modern digitizing scope to look at signals that are being produced at 2 dramatically different frequencies. I used an example here at 1.5 kilohertz and 15 megahertz, factor of 10,000 difference. And we looked at that on digital scope and how we had to play with record length in order to ensure the sample rate was high enough not to alias either of the signals. So I thought I'd do a quick video to show you how we did this old school with the old analog scopes. So I got the same 2 signals. Now coming over to this analog scope here. This happens to be a nice special scope. It's a Tektronix 2467. So if we look here, I've got the 1.5 kilohertz signal coming in here, the 15 megahertz signal coming in here. So right now I'm looking just at channel 1, and there's my 1.5 kilohertz signal. If I put on channel 2, I'll turn channel 2 on here. Now I can kind of see that a higher frequency signal just sitting back there as fuzz. And of course I could just expand the time base and turn the brightness up, intensity up here a little bit, and I can easily see the higher frequency signal there as well. Okay. But it doesn't, again, we're not be able to look at these things simultaneously and see the wave shapes of both of them simultaneously in this mode. I can really kind of look at one or the other. So let's bring this back down again, bring the intensity down. There we go. Let's see. There we go. So now, I can just see one or the other. So there is a way of actually seeing both, and the way to do that is to use the delaying time base. Okay, I did a video previously on the delaying time base and what it does, but what it allows me to do is basically take a small portion of what we see here and expand it out into a second sweep called the B sweep. So right now we're looking at the A sweep. In order to enable the B sweep, we pull on the seconds per division knob. That enables the B sweep here, and we start adjusting the B sweep. And as we do that, we see a highlighted portion of the display kind of getting smaller and smaller, because we're now, you know, yanking that small piece that's highlighted here and showing it to you down here. So if I keep going faster and faster with that delaying time base, you can see the value of it right here. Okay, so we keep going down here. Eventually I can actually start to see the high frequency waveform that's in that little sliver right there. It's not very stable, so what we can do is stabilize that. Right now, if we look at the triggering controls, okay, the A sweep is doing an auto trigger, and it's triggered on the vertical mode, which is alternating between channel 1 and channel 2. Let's hit this button here, and I can see what the B sweep is doing. The B sweep is being triggered right now on just to run after the delay that we've got set up here. We can adjust the delay of the position of where we're actually making that measurement. Okay. But I don't want it to run after the delay. I want it to be triggered, so I'll tell it to be triggered. Okay, and I'm triggering on channel 2, which is the high frequency signal. So now if we look at this on the display, I can adjust the delay and look at the signal at any point in time there, and what you see is this signal that's riding up and down. That's where this low frequency signal is at that instant in time. Okay, and then as we go through, we can see the 15 megahertz sine wave sitting in there. Let's expand out the time base a little bit more, make it even easier to see. So now at this set of time bases, I've got about a factor of 10,000 difference between the time bases. You can see 200 microseconds and it looks like 20 nanoseconds per division. Can't get it quite to focus right on that. Okay, but I can very easily see both of these waveforms. The low frequency waveform here sitting on top of the high frequency waveform, and then taking this little sliver of time and expanding it out at 20 nanoseconds per division and seeing the high frequency waveform along with the low frequency waveform kind of riding in there. So before the era of digitizing scopes and looking at signals like this, there were certainly ways of doing it with the analog scopes using a dual delayed time base. In this video we're going to take a quick look at characterizing this little Wiltron RF power detector I picked up at a Hamfest a few weeks ago, just to be sure it's doing what we expect it to do. So in order to characterize that, we're going to generate an RF signal here. It's just a pulsed RF signal, carrier frequency of 100 megahertz. We're pulsing it at a 3 kilohertz rate with a square wave, so it's just creating a series of RF pulses. If we look at it here on the scope, I can see, you know, it's basically just a pulsed RF signal. So the first thing we want to do really quick is just to take a look at the rising edge of this RF pulse and the falling edge of the RF pulse to ensure that they're going reasonably quick, so that we can you know, see what the actual response is of this detector, and not just following what the RF is doing. So we can kind of just use the delayed sweep here to kind of zoom in on that. So we just again activate the delayed sweep by pulling on the knob and adjust our B sweep. You can see we're kind of highlighting it on a certain area here. So I go down to say 200 nanoseconds of division, and I'll adjust the delay here as I go across. We can actually see that falling edge of the RF signal. Let's zoom in a little bit more here. So it looks like we're falling, you know, a little well within, say, about 100 nanoseconds or so. So that's not too bad. But in most cases, we're more interested really on the response of the rising edge anyway. You know, when the RF pulse comes on, how quickly is this detector going to follow that? So let's scoot over and look at the rising edge. Okay, so just adjusting the delay here until we get to the rising edge. If I kind of pull in here, there's the rising edge. So I can see this thing's coming up pretty quick. In fact, if we zoom in a little bit more, there's 20 nanoseconds of division. Move my delay over. If I look carefully, this thing looks like it's rising. It looks like essentially right at the first cycle. In fact, what we'll do is we'll tell the B sweep to be triggered, and so we can actually take a look at that, and I can actually see that, yeah, we're triggering, or you can see we're coming up to basically full amplitude right after the first cycle. So this thing has got a very fast RF rise time. So should be sufficient to do what we want to do here in terms of characterizing the speed of this detector. So I've got the detector loaded currently into 50 ohms. This is going to give me a very fast response because the detector is essentially a series diode with some shunt capacitance that's it's dumping the detected RF into. That's going to be in parallel with the capacitance on the scope input as well. Okay. So, but now with the scope impedance set to 50 ohms here, that 50 ohms is going to bleed off that cap really quick. So, so we're going to get a a quick response both on the rising and falling edge, even after the pulse goes away. And the rising edge is really going to be limited to by the series diode impedance and the capacitor that's there. So let's add channel 2 in here. Okay, so now I can actually see channel 2. And if we look at this, I can actually see, there's the rising edge of the RF. This is the negative going detector. So I can actually see the detector coming down. Now I'm looking at, say, 100 nanoseconds of division here. Let's kind of zoom it out to, say, 50 nanoseconds of division. Move this over. So I can see the response of this diode, this detector. It's coming down within between 50 and 100 nanoseconds. So that's pretty good. And because I'm in this 50 ohm load impedance here, I can actually see the RF ripple, if you will, because we're discharging that cap between each RF cycle, so I can actually see that going on. So I'd expect that, but that's good. Now if we scoot over and look at the other edge, okay, if I kind of all come across here with the delay, look at the RF falling edge, I can actually see that we're kind of almost following that here as well. And I kind of expect that because we're discharging that cap so fast with that 50 ohm termination. So, but what's interesting with this scope is that we can look at that rising and falling edge simultaneously. We can put this into kind of a dual delaying sweep mode. But right now we're in kind of a single delayed sweep where I can just kind of move the delay across and make measurements at different areas. Okay, but what I can also do is look at the other side. If I hit the delta T button here, okay, that brings up a second delayed sweep area. So if I put that on, you can actually see it comes up with another bright spot over here, and I can move that one separately. See, I've got one here and one here. I can move them independently. So if I move one of them here to look at, say, the RF falling edge, bring that up on screen. Let me get that zoomed in here. There we go. Right about there. And if I move the other one in here and look at the RF rising edge, there it is. Let's kind of get that one on screen. So now I've got them both on screen, but they're kind of overlapping. It's kind of tough to see. So this is where we switch from doing an alternate between the A and the B sweep and just go to the B sweep, because that'll give me both those delayed features. And I do that by simply pushing the horizontal sweep knob here back in again to just give me the B sweep. And when I do that, I'll kind of switch it back and forth. We can see we go from alternating A to B to just the B, and those are the two independent B sweeps. So one of them delayed so that I can see the falling edge of the RF, and the other one delayed so I can see the rising edge of the RF. And so I can see both of those responses. And that's about what I expect to see. Not a huge response, only about 20 millivolts or so on this 1 volt peak-to-peak RF input, but that's about what you'd expect to see when loaded into 50 ohms. Okay. Now let's kind of go back and look at this again. I'll turn the second delay off, and what I'm going to start off by doing is switching over now to instead of a 50 ohm load, let's go into a 1 mega ohm load. So if I go into the 1 mega ohm load, the response is going to be much bigger. So let's go change our volts per division setting here for channel 2, and I can actually see, this is now the response of the detector. And it's kind of what we expect, because the rising edge, when the RF comes on, we're basically going to dump some charge through that diode into the capacitor. Okay, and that's what we're kind of seeing here. But then when the RF goes away, that capacitor is left to discharge through the 1 mega ohm input impedance here. So it's going to get a very slow fall time. But I'm really more interested in what my rise time is, or in this case it's the fall time of this edge, but it's the response to the rise time of the RF signal. So let's go zoom in on that. Okay, so if I work my way over and find that rising edge here, Okay, I might have to slow this down a little bit, grab a little more time. Okay, and a little bit more. Okay, there we go, and I can actually go see that. And I just need to bring that trace up here a little bit. So, so I've zoomed in on that a little bit so I can actually see that response. Okay, and we kind of move that over here. We're looking now at 5 microseconds of division. So it looks like I'm going, you know, this is the zoomed in portion of that edge, right? So if we look at this, we go 5 microseconds, 10, oh, between 10, you know, 10 and 15 microseconds of a rising edge. That's not great, but it's not horrible. It depends on what kind of system you might be working on and whether or not a 10 or 15 microsecond response time is adequate to characterize a you know, particular RF pulse, or to provide a trigger on an RF pulse in a scope, for example. But it's all going to depend on repetition rate and things like that in terms of what that signal is doing in order to be able to, whether it's usable or not. But the way these power detectors work, their response amplitude and also the response speed is going to be a function of, you know, the load impedance into them. So, you know, we did a fairly big extreme here from going from 50 ohms to 1 mega ohm, and obviously we'd get a kind of a response that's in between these two that I've shown you here if you set their impedance to something else. But this is certainly enough to tell me that this detector is working as expected, and I can use this as I need to when I'm looking at some pulsed RF signals. One of my YouTube viewers recently asked me about a problem that he was having in looking at 2 signals that are set at the same frequency, and but not being able to view them in a synchronized way on his oscilloscope. And how do you get around that? So whether you're doing it with a digital scope or an analog scope, there are ways in many cases to actually look at stable waveforms. So what we've got set up here is I've got a signal generator here that's putting out a signal at 10 megahertz. That's coming out here. And we've also got another signal generator up here that's also putting out a signal at 10 megahertz. Okay, I've got them going into a couple of scopes here, digital scope over here, an analog one here. Well, let's take a look at these signals. I'm going to pull them off of here, and let's go bring them up to this frequency counter up here. If I stick one in the counter, okay, I can see that's 10 megahertz. I love these old Nixie tubes. And let's put the other one here in the counter. That one's also showing 10 megahertz. So they look like they're pretty close, but that's only showing me 5 digits of resolution. Got another counter down here that's got a couple more digits of resolution. So let's couple one of them in there. So that's showing 10 point, and it's going all the way down to 1 or 2 flashing in the last digit there. Let's look at the other one here, and that one's showing the same thing. So as far as these 2 counters can see, these signals are pretty darn close to the same frequency. But as it is in life, nothing is perfect. So we put these signals back into the scope here, and then we'll see that, you know, if we trigger on one, the other one is kind of moving because there is a very, very slight frequency difference. Okay, so how do we look at that? How do we actually, you know, stabilize the response there? Because I'm triggering on this channel up here, so this one is moving because there's a very slight frequency difference. We can see that walking. And of course, if we even count how long it takes or how many cycles go by per second, we can actually measure the frequency difference. But if I change the triggering to the other channel, now that one becomes stable and the other one is walking. Okay, so I can go back and forth. So what's happening in the scope is we're alternating back and forth between channel 1 and channel 2, but we're only triggering on channel 1 or channel 2. So the other one is going to walk because it's not synchronized to the first, because they're not phase locked together. But the way to get around that on a lot of scopes, certainly on a lot of the Tektronix scopes, you have the ability of telling the trigger source, okay, to not only be either channel 1 or channel 2, but also in this case there's a position called norm or normal. And what that will do is we'll take whatever you've got set up as your vertical mode. In this case we're alternating between channel 1 and channel 2. We can also have the trigger source alternate between 1 and 2. So if I simply push that up to norm, both of these now become stable because I'm triggering on one, and on one for one sweep and then the other for the other sweep. So that's how to stabilize that on an analog scope like this. Now the name of that mode will be a little bit different on different scopes. So what I'm going to do is I'm going to take these two signals, we'll move them over to a newer analog scope to kind of show you the difference over here. So let's kind of go down here, and I'll put these signals into this 2465 series scope. I've got the same thing going on here. One is walking with respect to the other. We look at the trigger controls over here. You see I'm triggering on channel 1. If I move that to trigger on channel 2, okay, now I can see the other one is stable. If I go back to channel 1, and then so I can go back and forth, you know, and see trigger on one and be, you know, not stable on the other one. But on this scope, instead of that mode where we're going to follow the vertical mode being called norm, on this scope it's actually called vert, V-E-R-T. So we're going to follow the vertical mode. So it's just a matter of pushing the source button up one more time to select that mode, and now we're both stable, because now we can see that the vertical mode, or the trigger mode, is actually on this thing called vert, and we can see it's alternating between channel 1 and channel 2. And you can see a nice stable display. If I pull back here, you can see if I change that back to channel 1 or channel 2, it's just moving back and forth. If I push it up again to go to the vert mode, both those lights are lit up over here, and I've got a nice stable display. So on some analog scopes, I've got an older Heathkit analog scope here that does not have that kind of a mode, so there really isn't a good way of stably triggering on these two signals that are very, very close in frequency. Okay. Similarly, a lot of the digital scopes don't have that vertical mode either, that trigger capability. So if we look here, if I can get in here so I can see it, I'm triggering on channel 1 here right now. Okay, so we can kind of see that nice and stable. If I move my, if I go to the trigger and tell the trigger to trigger on, say, let's get that to focus on channel 2, see now channel 2 is stable and the other one's moving. If I go through the choices here, you know, I can go to channel 3, I can go to channel 4, I can go to external divided by 5, AC line, and back to channel 1. So I don't have that alternate type of trigger mode where I can sweep back and forth. But the really simple way to do this on a digital scope is to recognize that whenever we get a trigger, we're getting a sampled record of both signals. Okay, and what we're looking at with this thing rolling is multiple acquisitions. So all we do on the scope is go to a single sequence. So I just basically capture one event. So now we're essentially, if I hit it again, we'll do another capture. Again, we'll do another capture. So each acquisition is going to be, you know, give you a stable result for both waveforms. So that's how you typically would do it on an analog scope, is just do a single acquisition and then go make the measurements and comparisons and things like that. Whereas if you're running or triggered on one or the other, you won't be able to see them stably. So we can take a look here. We can see there's probably a 1 or 2 hertz difference between these two signals in terms of how fast this signal is moving with respect to the other one. So if I take both of these signals, I can bring them up to, this counter here is a bit more high resolution, so I'll couple one into one channel here. I'm going to couple the other one into the other channel here. Okay, so right now we're looking at the frequency of the signal on channel A, so we're 10 all the way down to about 1.7 hertz higher than 10 megahertz here. Alright, and if I go and change, if I tell it to measure a frequency, and I want to measure a frequency on channel B, okay, right here, okay, and that's showing 10.000 and then about 4 hertz. So I've got about a little more than 2 hertz difference between those two signals. Now, you know, that's a small enough difference that I was not able to see them on the older, lower resolution frequency counters, but in this one I can see it very easily. And again, if we watch the display here, you can see that you know, how fast are these, you know, are these cycles walking past each other. So if I say 1/1000, 2/1000, it's about 2 cycles worth of drift that we're getting in a second, which would indicate about a 2 hertz difference between these two signals, and that's kind of what we're seeing. So again, if I go tell it to measure a frequency, and I'll measure a frequency on channel A, that one is just under, you know, 2 hertz high, and the other one's about high, so there's a 2 hertz difference. So that's how, both on a digital scope, single sequence, or on an analog scope using, you know, either a vertical mode driven trigger, or like on the Silver 465B, using the normal trigger mode. That's how you would actually go and change or set up the scope to give you a stable response on two signals that are very closely spaced in frequency. Okay, this video is going to take 5 minutes or so to kind of talk about what this new Tektronix MDO, Mixed Domain Oscilloscope, is all about. Basically, it is a 4-channel analog, digitizing oscilloscope. These channels will either be 500 megahertz or 1 gigahertz of bandwidth on all 4 channels. 16 digital channels, 20 meg of memory behind all of those channels, but then also adding a either 3 or 6 gig spectrum analyzer to the box. Okay, so basically it has all the features that you typically expect to see of a mixed signal oscilloscope, adding all the channels, turning them off, but also now adding a spectrum analyzer to it. We hit the spectrum analyzer channel, and it basically splits the screen to a time domain and frequency domain. If we turn the analog channels off, we basically get just a spectrum analyzer, and it drives just like you'd expect a spectrum analyzer to drive. We can do your typical spectrum analyzer functions: frequency, span, bandwidth, resolution, bandwidth, things like that. Very easy to kind of go show, what the spectrum analyzer can do. Some very interesting things that your typical spectrum analyzer doesn't have. Things like a spectrogram, which allows you to look at how spectrums are changing over time. In this case, I've got this spectrum kind of wiggling around here a little bit over time. And if we look carefully at the spectrogram, we can actually see, how we're just basically chart recording that into the spectrum analyzer display. But because this instrument is oscilloscope based, we do have the ability of showing additional RF capabilities versus time by looking at things like RF amplitude, frequency, or phase versus time. You can almost think of those as AM, FM, or PM demodulators. The signal we're looking at is a frequency modulated signal whose baseband is ramping back and forth slowly. So if I turn on a frequency versus time trace, the upper trace here becomes essentially frequency deviation versus time. Okay, so lots of feature-rich displays here, looking at things in a number of different domains just on the RF channel. That's all I've got turned on right now. But really the power of this instrument is the ability of tying in data captured on the RF channel to capturing that data and tying it into both data captured on the analog channels as well as the digital channels, all done simultaneously. So let's take a look at some of that capability. Okay, so we'll switch the demo board over here and go take a look at an interesting setup here. So I'm actually probing a number of different areas on this board. Okay, and we'll take a look at this. I'm probing a couple of analog signals here, channel 1 and channel 2 on the scope. I'm probing some digital lines over here with the digital probe, and I'm also got the RF output being coupled into the spectrum analyzer input. And what we're simulating here is actually the behavior of a phase lock loop circuit. What we're doing is basically captured a couple of channels along the top here. We can see I've actually, channel 1, we're calling it a PLL enable. We're actually enabling this the PLL circuit that's on here. The next voltage that's coming here on channel 1. Channel 2 right here is the VCO tune voltage. What we're doing is commanding the PLL to tune to a new frequency, and we're watching that happen. Down just below that is a SPI bus. We can actually see the SPI bus there, and that's actually a serial command that's sent to the PLL to tell it to tune to a new frequency. We've captured all those over time during this startup and tune behavior. Nothing's new with that, but the idea is we've also captured the RF activity at the same time. And the way we time correlate all this together is this spectrum that's shown right down here is being shown at this location right here where that little orange bar is. We call that the spectrum time. And by using the navigator, wave inspector controls here, I can just move this pan control, and if I move that, we can actually see how I can move that spectrum time back and forth. So if I move it over to here where it was, I don't see anything in the spectrum because this is now lined up before the VCO is enabled. So if we move it after, now I can actually see the RF signal came up, and as I move it through in time, we can literally see how the spectrum of the RF signal is changing over time. So I've captured the complete seamless RF history of the data going on in the RF spigot, as well as the analog channels and the digital channels, all time correlated here. And we do, of course, have the ability to zoom in like you do with the DPO and MSO products. In fact, if we zoom right in, right here where that SPI bus command is, we can actually see the decode of the SPI bus right here. If we look carefully, I can see what I triggered on. It's actually a 203141 hex. In fact, if I hit the trigger button here, I can see I actually triggered on that data value of 203141 hex. I was able to tie all that together. And I can zoom back and forth here as well and see all this activity. If I look at some of those RF versus time traces, if we go back here and I add RF versus time and I turn on the amplitude versus time, the amplitude versus time trace just popped up right there. I'll just move the scale that up a little bit. So now I can actually see the delay from the enable signal going to the PLL and that signal coming up. So that's really the idea of what the MSO is all about, or the MDO is all about, being able to tie analog, digital, and RF time domain all together in one instrument. Right, this video is going to show a quick example of how we can use the Tektronix MDO 4104 to capture some off-the-air 802.11 traffic. We'll export that data to an IQ file and bring it over to a PC for analysis. So basically, I've got the instrument set up here. If we take a look at the spectrum analyzer controls, let's hit frequency and span, and we can see I've got center frequency dialed in to, actually look at it down here, 2.462 gigahertz, which is channel 11, which is where my wireless router is transmitting. I've got a span of 40 megahertz. I've got a reference level of minus 35 dBm, and I just have a simple little whip antenna sitting on here. So we can see some activity going on from my router, from the other computers in the house here. What we'll do is we'll capture some of this over time. And the way we'll do this is we're going to use the RF input to do a trigger. So I'm going to hit the RF button here, which will bring up a menu down at the bottom and allows me to add, say, RF versus time traces. And I'll add the amplitude versus time trace. Okay. And I can actually see I've actually got a transmission that I just captured here. That's an RF amplitude versus time. Okay. And we can actually see I got two little bursts. Actually, I've got a couple of other ones coming in here. That's probably a Bluetooth thing popping in. What I'll do is I've got this set to kind of free run, so each time we trigger, we capture a couple of things going on here. In fact, we could, if I walk my way through here, we'll do a single acquisition and go do that and see what we've got going on. So what I'll do is I've got this set up for an RF power trigger. Okay, so if I hit the trigger menu, we can see I'm triggering on doing an edge trigger on RF power, rising edge at minus 30 dBm. Okay, I've got this set up for 40 microseconds per division, so I'll capture 400 microseconds worth of activity. And what we'll do is I'm going to set the instrument up to do a single acquisition. Okay, and we'll grab my iPhone here and see if we can cause the iPhone to make some to capture some data. So there we go. We actually captured a transmission here. I can actually see the iPhone, which is this bigger one right here, and then my router responding there. This vertical scale is linear as opposed to the spectrum analyzer, which is logarithmic. So we can see how much lower the router signal is. What we'll do is I'll do another one here real quick. What I'll do is I'll tell my phone to go grab an email. I can actually see the transmissions there. We could do another single again, and do it again. Go out and grab an email. So now, so I can very easily capture some of this RF activity. If I walk through this, move this spectrum around, we can actually see that there's the spectrum from my iPhone, and then if we move over, there's the spectrum from the router, and then the spectrum goes away. Keep moving over, there's my iPhone again, and there's the router, and it goes away. All right, so now I've got this data collected in here. Let's go transfer it over to the PC. So I've got a memory stick in here, so I just hit the save menu, tell it to save waveform, and I can select here to save as baseband IQ and hit OK. Okay. So now I've saved that off to this memory stick here. Okay. And if we pull that memory stick out, and we'll bring it over to my PC, stick it into the PC here. Okay, and let's take a look at, I'm going to just take this file, and I did this a couple of times, so I've got this number 4 here. I'm just going to transfer this TIQ0004 over to the desktop. There it is. and I'll go into the RSA view application here, okay, and I'm going to tell it to load that file in, that TIQ004 file. So I'll just tell us to, I'm going to go over here to load, okay, and I'll go over here where it says load data from TIQ, and I'm going to tell it to go look at my desktop. So let's pull this back so I can see what I'm doing here. So it's screwed up here, and go to desktop, and I'll open that folder, and there's the file right there, 04TIQ, and I can hit done and load file. So now I've got that file in here. If we look at the spectrogram, I can kind of see that. If I walk through this, I can see those same spectrums that we were looking at earlier. Okay, so now I've got the data loaded in here. Now I want to go analyze this, and I'll go over here and hit DMOD. Okay, that brings up this over here, and I'm going to go and do a standards-based DMOD, and I'll go down to the next menu here to give me 802.11 A, B, and G. Okay, so if I look at that now on the screen, I can see there's my amplitude versus time. You know, I can see the burst from the iPhone, burst from my router, burst from the iPhone, burst from the router. Now let's say I want to only analyze, say, this portion of it, say from here to here. I'll just double click and single click, go over here and say marker 2, and now it's time to go marker time. I'm only going to analyze that one burst. Okay, we're looking at right there. Okay, so if we go over here to measure, well, let's pick a measurement, maybe how about subcarrier constellation? Okay, and I'm going to go tell this to analyze. Okay, now I can actually see the constellation diagram. Okay, at a particular point in time, in this case it's at the tail end. You can see my marker is sitting right here. So I'm looking right at the tail end of the my wireless router's burst. I can see this was an OFDM 24 megasymbol per second constellation. I can see the pilot tones in here as well, the pilot constellation points in here as well. And if I move my marker around in here, I can look at the constellation in different areas. So if I scoot over to, in this case I'm now looking, if I look carefully I can see the marker is sitting in my tail end of my the burst from the iPhone. As I move this back and forth, you can see the constellation moving back and forth here. I'm trying to get this to focus. So I'm analyzing, is the subcarrier constellation, I'm looking at that. So I got all the, in my measurements, I've got other measurements I can go make here, but this just shows how you can take TIQ data from the MDO and go in here and do your analysis. Want to look at EVM versus subcarrier, we can go look at EVM versus subcarrier. Want to look at power versus subcarrier, I've got that in here as well. Subcarrier constellations, and I can go in here and pick, you know, what symbols I want to go look at. As I just walk my way through, you can see the constellation change as I walk through the different symbols through the different bursts. Okay. So that's a quick example of capturing some off-the-air 802.11, loading it into RSA View for analysis, and then being able to look at that in multiple domains here in RSA View. Well, my recent Hamfest find of this Tektronix 1401 Spectrum Analyzer module is just kind of a fun little box. And as I may have mentioned in the previous video, the interesting thing about this module is it was available, or it was typically sold along with a little 323 battery-powered oscilloscope that was virtually the same physical size in terms of dimensions, and the handles linked together. And the nice thing is both of these things were battery-operated, and it made it really popular with people doing surveillance and looking for bugs and doing all kinds of RF surveillance and things, because it let you get out in the field and make measurements without having to be plugged in somewhere. So it was kind of neat. It has a really neat little feature that I haven't seen on modern spectrum analyzers, which I thought was pretty cool. Part of the problem with some of these older analyzers like this is that when you put them onto the scope, nothing was really annotated. So if you're looking for a signal, what would you do? So this had a really neat, what they call a search feature. And if you look at the frequency span control here, and if I adjusted that all the way down to the bottom one, which is 50 megahertz per division, they also called it a search mode. Okay, and what that did, I'm going to switch it back up to 1 click here, or 2 clicks before that, and look at the spectrum analyzer display. Okay, if we look at the analyzer display here, okay, so that's at the 10 megahertz per division. I don't see a signal here. All right, so let me turn the intensity down a little bright here. There we go. I don't see any signal on here. I've got a signal going in, but I don't see it. So a lot of times what you might do is, if we go all the way over to that search mode, you'll notice I see a couple of signals here, and you'll notice that little notch section down at the bottom. That's actually kind of what we call the kind of the search marker. All right, and the way that worked is it allows you to essentially adjust the center frequency control here, which is also called the search marker. And a real good way to make that stand out quite a bit, if I pull back here and watch, if I switch the video bandwidth filter, let me switch the video bandwidth filter on, and you'll see that kind of eliminates a lot of the noise from the video output. So I get this little notch, okay, and if we kind of pull this guy up here, let's kind of pull back a little bit. If I adjust, you can kind of see that notch on the display. If I adjust the center frequency, you may notice that that notch is now moving back and forth. So what the guys out in the field will be able to do is, if they saw a number of signals on the display, they might say, well, yeah, there's a signal, say, over here, there's another one over here, over here. I want to go see what they are. What I would do is, by adjusting the knob here, I can adjust over to be centered up on that particular signal, say right there. And then I could look here and say, okay, that's right around 149, 150 megahertz. And then by taking my span control and zooming in, okay, let's grab the right knob here, and now I can really zoom in on that particular signal, go finer and finer in terms of fewer megahertz per division, and get a finer look at that signal. And I can adjust the resolution bandwidth down and maybe look at a finer result of that. So that kind of search marker, along with, and the video filter certainly helps too, right? The search marker and the video filter are really helpful to kind of, let's see, get this thing to focus here again. There we go. Put the video filter on, see how it gets rid of all the noise. Okay. So between those two things, made it really easy to kind of go and pick out signals. Just kind of a unique thing that, that it was kind of a predecessor to some of the more modern spectrum analyzers that actually had marker controls that you could put on the display. So before we had that, in terms of figuring out where you were in frequency, that little search marker notch, if you will, I thought was a pretty unique feature that, like I said, I haven't seen typically on other analyzers. Just kind of a unique thing. I thought it was pretty cool to do a quick little video on. But anyway, just fun stuff from the mid-70s. Anyway, hope you enjoyed. Alright, in this video we're going to show how we might be able to use this new Tektronix mixed domain oscilloscope to diagnose a transient EMI emissions problem with a printed circuit board here. So I've got the spectrum analyzer on here. We're using this little near field probe. This is call it an H-field probe. It's a little magnetic loop. These are available in different sizes from different manufacturers. This one happens to be from Electrometrics, but there's a lot of other nice ones made by companies like Beehive Electronics and a number of other folks. So the nice thing about this is that you can kind of use this to kind of zoom around on your board and look for issues. So if you just take a look at the spectrum analyzer here, as I kind of probe around, I can see, well, over in this area of the board I've got a lot of broadband kind of digital noise. You see all the little spikes in there, kind of indicated probably some kind of a data pattern or digital pattern, high-speed data or whatever, or clock. If I come around to different areas of the board, as I kind of scroll around, you can see different areas coming in. And the thing that kind of caught my eye was, if I lay the probe right down in about here, okay, let's see, right about there, I've got this little spiky little thing that's popping up right here. It's moving about 10 to 15 dB and popping up every once in a while. And maybe you're in a situation where signals below this level are okay, but when this thing kind of pops up there, that causes a problem. So we can actually use some of the tools available here with this MDO to kind of try to isolate that issue. And if we get lucky, we might even be able to trigger on that and then to go looking around on the board. So let's set up and trigger on. Try to see if we can do an RF power level trigger on that thing. Since that's increasing by more than 10 dB, we've got a halfway decent shot at doing that. So we can go into the trigger menu, and I can do an edge level trigger. Right now the edge trigger is looking for something on channel 1, but I can actually change that to show RF power. So if I were to use RF power as my trigger source, so let's go down to RF power as my trigger source. Okay. And I'm going to change the spectrum analyzer to change from running free run to triggered. So now that I've triggered, now I'm seeing that high level power here consistently on the spectrum analyzer. Now I've got I can go see what's going on, maybe at some other domains. So what I can do is take a look at what's going on this board and maybe probe around with a probe to see what's happening. So I'll add channel 1, but before I even do that, let's go see what we can learn just from doing a simple time correlated capture here. So I just do a single little capture. So right now there's that peak I'm interested in, and that's occurring at this point in time with respect to, I'm just looking at kind of a ground signal on channel 1 here, but I can move the spectrum time, and if I move this across, we can see that peak is going away. See how that peak went down about 10 dB as I scroll this thing across. As I keep scrolling, okay, you're going to see that peak come back up again. Okay, there it is. Oh, I just went right past it. Let's bring it back up here. So let's go back a little bit. There it is. That peak popped up right again there in time. So between these 2 points in time, I've got this spike popping up. I actually kind of already set up some cursors to kind of show that repetition interval. So the peak, that spectral peak that we're looking at here, pops up here in time and here in time. A difference of about 96 microseconds. Okay. So now that we know that, we can go and look, on the board for something that is repeating at that rate, and maybe try to isolate what might be causing that event. I had already done some probing around on this board, and what I had found was there's this header called USB HS, or a high-speed USB port. If I go and move my probe over to there and take a look up on the scope, I can see that I've got this burst of data that's occurring at that same rate. Okay, let's do a single shot capture on this, and you'll notice if we kind of scroll the spectrum time around, I can see that in between here, that peak we're looking at is kind of dropped down. If we kind of get back onto this high-speed data burst right here, there it is, it popped right back up again. Let's go look at that one over there. I'll scroll all the way over there and look at that one. When I get up there, boom, guess what? That spike comes right back up again. So what we found is that on this board, in this area of the board, we're emitting the signal at, let's throw a marker on there, at about 137 megahertz. Okay, that's popping up by 10 or 15 dB. Okay, each time this USB HS burst is being transmitted. And we could do things like zooming in and taking a look at what that data looks like, but there's a quick example of being able to use some of the tools and multi-domain capability in the mixed domain oscilloscope to track down some kind of a transient problem that might cause you to have some EMI compliance issues. Yeah, sometimes I have folks ask me, especially some ham friends and things like that, they're saying, I want to pick up an analog scope for doing some stuff in my my bench and just experimenting with circuits and repairing things. How much bandwidth do I need? And I usually answer, as much as you can afford. And say, well, I'm just working on, radios or amplifiers, and, I might be working with just audio circuits and things like that. So, can I get away with, a 10 or 20 megahertz scope? And I say, well, maybe, maybe not. So in playing around here on the bench, I came up with an example to kind of illustrate, why you might need more bandwidth than you think. It's a good idea to have. So I've got this little simple phase shift oscillator circuit that I put together. It's a single transistor, simple biasing here to bias the transistor up, create some gain, and then a phase shift network to create some positive feedback to cause this thing to oscillate. And this creates a reasonably good audio oscillator at, in this case, about 2.9 kilohertz with the values that I've got shown here. Okay, I've got the circuit built right here. You kind of see there's the transistor, the caps, the resistors, etc. I'm probing with this probe right here, right at the output right here, over onto the scope. And if we take a look at the scope, there's the output. So it's a couple of volts peak to peak. And if we look, that's 100 microseconds per division, so that's in the neighborhood of 2.9 kilohertz. So everything looks pretty good. And but what I found was I've got the scope dialed down. You can see this little BWL down here. That says I've got the bandwidth limit turned on. If we look over at the front panel of the scope, we've got the bandwidth button dialed in here. And if we look carefully, you might be able to see that says 20 megahertz. So basically this is acting like a 20 megahertz scope, even though the full bandwidth of the scope is 350 megahertz. So everything looks kind of good. And if I turn the bandwidth limit off, okay, well, it doesn't look much different. The line gets a little fatter because there's a lot more bandwidth now. We've got 350 megahertz of bandwidth, so I could be getting some noise. So that little growth and fatness of the line there could just be due to excess noise that we're filtering out when we go down to 20 megahertz bandwidth. Could be, maybe not. So let's look at another node in the circuit. Instead of looking at the base, or excuse me, the collector here where the output is, I'm going to look over here at the base, the input to the transistor. So let's move the probe here over to there. Okay, so now we've moved that over. Let's go over to the scope and let's crank the sensitivity up here a little bit. And let's see, play it by triggering a little bit here. Let's knock that down there, and here we go. There it is. So there's the base drive going into the circuit. Right, everything looks good, but I've got the bandwidth limit turned on. Now let's turn the bandwidth limit off, and look at that. I got these big fuzzy, kind of almost heart-shaped things going on here that when I have a 20 megahertz mode here, you just can't see. So what that tells me is that there's some spurious oscillation going on at these portions of the waveform here that's well above the 20 megahertz bandwidth, because the 20 megahertz bandwidth is knocking it out. But that's real. Okay, there's a real oscillation going on there, and that's probably contributing to the little fuzziness we saw in the output, but that's really going on. Now, how high is that frequency that we're looking at here? Well, what we can do is we can kind of expand in on that and look at that with the scope here. So I'm just going to use the delayed time base here, okay, to kind of pick out a small portion of that waveform. Okay, you see the little dot I'm moving around back and forth there. I'm going to move that into that portion of the waveform. Let's expand that out a little bit. So now I'm looking at about 5 nanoseconds per division on that expanded portion of the trace, that little piece right there. I'm expanding out here. And looking at that 5 nanoseconds per division, I've got about a 5 nanosecond period of that of that oscillation that's in there. A 5 nanosecond period, that's about a 200 megahertz oscillation. So even though this circuit that we've built is a 2.9 kilohertz audio oscillator, there's, during portions of this the cycle when this thing's going through, it's singing at over close to 200 megahertz. Well, could that cause a problem? Well, I mean, you might create emissions and things like that that could interfere with other portions of the circuit. You could dissipate extra power. You could upset bias of other circuits. You can couple into other things. And how would you know this? If you just had a 20 megahertz scope, everything would look normal, right? But with the wider bandwidth, you can actually go see that. So that's where it's beneficial sometimes to have more bandwidth than you think you need. And turns out it's a pretty simple fix for this thing, but part of the problem is that we're in these solderless breadboards, which are great for prototyping circuits, but they've got tons of parasitic capacitance, and they've got inductance, and they've got all kinds of coupling. They're really not great for anything that has the potential for doing high frequency stuff. The other thing that it's just kind of a basic thing of when you're building transistor circuits is you want to kind of have some kind of a lossy impedance in at least 2 of the legs, and really right now we've really got it only in 1. So if we throw some resistance in series with the base here, we can kind of squash that oscillation. So right now you can see it's kind of oscillating there that we were looking at here before. I'm going to stick a little bit of resistance right in this portion of the circuit here, and all I have to do is move this capacitor leg over here. I've already got it on the board, so let's see if I can do this and stick that back in there where she belongs. Stick that lead there, and then get that lead guy in there. And now if we go back and look at this thing here, let's go back up to our normal look at the base here. There it is. So there's our base drive. Now it's all nice and clean. Okay, no oscillation. Whether I got the 20 megahertz bandwidth on or not, everything's nice and clean. I've cleaned up the oscillation from that circuit. It doesn't exist anymore, but that's something that we wouldn't have found at all if we didn't have extra bandwidth on the scope. So again, the bottom line is, no matter what you're doing, it's always nice to have that extra bandwidth, because you never know when a simple little circuit like that could start singing at some really high frequency, and you really have no way of understanding it, seeing it, and then fixing it without having the tools to actually see it. So that's one thing to be careful of with any tool, no matter what it is, whether it's a scope or anything else, is understand what the limitations are. Okay, if you've got a 20 megahertz scope or a 50 megahertz scope or something like that, or even a digital scope, whatever it might be, you've got to understand what the limitations of those tools are, so that they don't lie to you. I mean, the scope wasn't really lying to me, but it was hiding the fact from me that I had this 200 megahertz spurious oscillation in there. So without thinking, if I didn't know that I had the bandwidth limit turned on, or if I didn't have a wider bandwidth scope, I never would have seen that. So always have another way of looking at your circuits and things like that, and make sure you apply some common sense to what you're looking at. But anyway, hope you enjoyed that, and have fun with your scopes. Well, my last video talked about analog scope bandwidth considerations, even if you're doing low frequency audio work, and why it might be nice to have more bandwidth than you think you need. We played with this little phase shift oscillator circuit here. I corrected the schematic. In my previous video I'd redrawn the schematic incorrectly, so I had the 200K resistor up here. So I put it down here where it actually is, and where I built the circuit. The circuit was intentionally built with kind of poor layout and poor component choice here on this little breadboard. These things are really bad for adding a lot of stray capacitance to your circuits, and coupling from one node to another, and inductance and things like that. They're not great for anything that has a potential for doing anything high speed, but we did that intentionally to show that sometimes what look like pretty simple benign circuits can do some weird things at high frequency. And we showed that when we probed the base here in this oscillator, phase shift oscillator, that we saw some oscillation that was kind of busting out, that when you had the scope set to a narrow bandwidth you didn't see, and then if you open up the bandwidth you did see it. There were a couple of questions that I had that the video raised, and one of them was really what happens with a digital scope, and what considerations do you have there. So we're going to talk about that. But the other question real quick that I had was, did the fact that I put the probe on this node add enough capacitance to cause the oscillation in the first place? Meaning, does the oscillation go away if I remove the probe? And the way to kind of see that is, rather than probing here, let's probe at the collector. Okay, and if I look over at the collector voltage, I can kind of see it right here. Okay, and that's with the bandwidth limit off and with the bandwidth limit on. And if you look really carefully down here in the corner, okay, you can see a little fattening of the trace and say, well, gee, is that same oscillation? And we can find that out. I can just kind of zoom in kind of vertically here and kind of see what that looks like if I kind of turn the bandwidth limit on or off. But then if we kind of zoom in horizontally, kind of the same deal we were doing before. Let me kind of scoot this down here and move my delay over. Okay. And let's see, I just need to adjust the trigger position here a little bit. And let's turn the bandwidth limit off. And so now I can actually see that band kind of being lit up here. And I can kind of see it here if we zoom in a little bit further. Yeah, lo and behold, there's the oscillation. It's still there. So at that same 5 nanoseconds per division, we're still seeing that same about 200 megahertz oscillation. So it really is there. It's not due to me probing, but that is something that you definitely got to be cognizant of, is that sometimes adding a probe to your circuit can add capacitance and loading and things like that can upset the performance of the circuit. In this case that wasn't the case, but it was a good question, so there's the answer to that one there. So let's take a look at on a digital side of things what's going on. So I'm going to take off my old analog scope here, and I'm going to grab the probe for my digital scope. This is also a Tektronix scope. This is a TDS 2014. Okay, this TDS 2014 is a 4-channel 100 megahertz 1 gigasample per second scope. You might say, well, I probably got enough sample rate to look at this thing, but 100 megahertz isn't enough bandwidth. Well, the reality is you still can see it. One thing to remember with when you think about scope bandwidth considerations is that if you've got a 100 megahertz scope or a 350 megahertz scope or a 20 megahertz scope, it doesn't mean that you can't see signals above that. It just means that they're going to be reduced in amplitude. So so the fact that we know this circuit's oscillating at about 200 megahertz doesn't mean we can't see it. Certainly we can. It just may not be at the full amplitude. But in this case, we don't really care too much that that's the case. But so we're looking at that same node there. And if we do the same trick, for example, if this was set to, let's turn that on. If this was set to, say, a 20 megahertz bandwidth, that looks like what we looked at on the other video. It doesn't look like there's any particular problem. But we look at the full bandwidth here, and we can kind of see that. Now, this scope doesn't have that dual delayed time base that we had on the old analog scope, where I can pick a region and set up a new sweep. But it does have, in the horizontal mode here, a way of setting up a window to look at, and then just be able to look at that window. So I can set this window up, and it brings up an area that I can define the width of that by kind of adjusting my knob here. Let me go back to my main here, knock that back here, and I can set up a window, and if I can make this narrower and narrower, and I can go down to about that same, look down the bottom, down to about that same 5 nanos per division, and where I've got it positioned right here. So then I can say, rather than display what I'm looking at here, let's display the window. Okay, and I can see the signal there. It's free running because I'm triggering on that slower signal. I'm not triggering on this, and that's one of the advantages of the old analog dual delayed sweep, is that the second sweep you could trigger on something separate, and I had actually triggered on this high frequency signal. But with the digital scope, the easiest thing is just to hit a single sequence, and then it stops, and there's our signal, that oscillation that's buried inside of that thing. I can't see them both at the same time like I could on the analog one on this scope, but you can see it. Okay, and if we look, we're at 5 nanoseconds per division. I've got about a 5 nanosecond period, here. In fact, I could put cursors up there and put the time cursors on, and we can kind of roll this around and say, yep, there's a peak there. Go over here, there's a peak there. And if we look, my delta is about 5.6 nanoseconds, 170, 180 megahertz. I didn't do a real careful measurement, but that indeed tells me that I do have that oscillation there. So yeah, so we can see it. Even on a 100 megahertz digital scope here, but the way you kind of zoom in to look at it is a little bit different. So that's an example of kind of who I would call kind of more of an entry-level analog scope. This one is relatively older technology by today's standards, but it's pretty common that you'd find a scope like this, and certainly that could be used to look for the same type of issue that we're seeing with the simple analog circuit. So I'm going to remove this probe. And let's look at a little bit more advanced scope here. This is a 4000 series scope. This happens to be the new mixed domain oscilloscope, the M0ODZ. But essentially, from an analog scope standpoint, it's a 4-channel 1 gigahertz scope running at 5 gigasample per second. So if we hook this probe up here, let's kind of hook my ground up here and hook the probe up to the same base node we've been looking at. Okay. So now I can see on this screen, okay, I've got that same kind of ugly looking thing, but I got this weird little banding going on. Now, one thing to think about with some of these more advanced scopes is we've got a little bit more flexibility in terms of things like, we've got a lot more resolution on the screen. We've got more flexibility in terms of sample rate. And if I look right down here, I'm looking at 100 microseconds per division, but the scope is by default is using just 10,000 points, so it's only running at 10 megasamples per second. So I'm pretty much undersampling that high frequency oscillation. And the way we can get around that is by just changing the number of points that we're using here. Okay, so if I hit the acquire button on the scope, I can change record length from 10,000. Let's bring that from 10,000 down to say like 100,000 or even 1,000,000 points. And if I look down the display now, I've got 1,000,000 points. So now that the scope is really sampling at 1 gigasample per second, so sufficiently oversampling that oscillation. And now in the waveform here, I can see that I don't have any of that kind of weird banding going on. Okay, and then once we've got this, it's very easy to zoom in. This scope has got this really neat feature called a wave inspector. What I'll do is I'll just do a quick single acquisition. So I've got an acquisition here in memory, and then by just rotating this knob, I can change the zoom level. You see, once I did that once, you see these brackets here. Okay, so now as I keep rotating this knob, those brackets get narrower and narrower and closer together. And now I'm zooming in finer and finer and finer into that particular signal. Okay, so now I can actually see, there's my signal. If I look down here, let's see, my zoom window is at 10 nanoseconds per division. Okay, and now I can actually see there I am. It's about a half a division, so there's my same 5 nanoseconds, that same 200 megahertz oscillation. Okay, so there's ways to do this with both the digital scopes as well as the analog scopes, and it just is a matter of being cognizant of what you're doing with your sample rate, your record length, and what you would have to do in the scope, whether it's to set up a new horizontal acquisition kind of setup here, like we did here using kind of a window, or going in and zooming in on a longer acquisition and ensuring you've got enough sample rate, or on the old analog scope it really came down to playing around with the dual delayed time base and triggering appropriately on the other signal. So anyway, I hope that answers some of the viewer questions that I had on this simple little analog phase shifter circuit, or excuse me, phase shift oscillator circuit, and different ways of looking at these high frequency problems you can get with both analog and digital scopes. So enjoy. Okay, in this video we're going to take a brief look at how we might use some of the features of a real-time spectrum analyzer to help find EMI and emissions problems with a circuit board, and how some of the tools and features of the analyzer can be used to help you out. So we're looking at a display here that we call DPX, Digital Phosphor Spectrum Processing. What this does is it gives you this multicolor display that is a composite result of almost 300,000 discrete Fourier transforms a second, and laying them all on top of each other and giving you this color grade of how often things are occurring. In this case, when we look at various colors here, the hotter colors like red and yellow are areas that are occupied most often, and the cooler colors are things that are like the green and light blue and dark blue are areas that are occupied less often by these 300,000 spectrums a second that we're looking at. We're going to do this by looking at this little near field probe. This one's made by a company called Beehive Electronics, just a little near field magnetic loop probe. We'll be able to kind of scoot this around over the board, and as we do that, we can kind of see what's going on in different areas of the board from an RF standpoint. The real-time analyzer is kind of literally showing you live what's going on in the spectrum as we kind of scoot across here. So we can literally see everything that's happening. We can see kind of these little transient little things that are going on like that, and steady state signals like these guys over here, transient types of things that are kind of creating the light blue haze above things there. So we can learn about all kinds of things. And we can set the RSA to do a couple of other things too. We can go over here and put on what we call a spectrogram along with the spectrum. And basically what this is the spectrum kind of moving and walking across. So as we're moving around on the board, if I pan back here far enough, you can kind of see if I'm moving around on the board, you can kind of see those changes going on the spectrum at the same time. So this might give you a quick idea as you're going through to be able to see things and understand kind of what's happening on the board there. But let's say we wanted to find a transient problem that we really want to go take a look at in more detail. What I'll do is I'm going to turn off that spectrogram mode, go right back to the normal DPX spectrum. Okay, so now I can see kind of everything that's going on here. And so one thing we'll look at, for example, I found this interesting one on the board here. I can see all these, these kinds of wiggly things like that guy going on right there, and say, what is that? It helps sometimes to kind of look at those in the time domain and stretch them out a little bit. And we can do that by going into displays here, and I'm going to add a spectrogram. So let's add the spectrogram to the displays here. And by doing that, what that does, we can take a chunk of data over time and then kind of stretch it out. And now if we look, say, at this little wiggly thing that's over here, if we look at it on the spectrogram, you can kind of see it wobbling back and forth. So that's actually a spread spectrum clock. You can kind of see the behavior of that just by being able to capture a snapshot of that over time, okay, and then being able to kind of look at that seamlessly in time to see how that's changing. So I can see I've got that spread spectrum clock. I got a couple of other CW things. If you look carefully, I've got a little bursty thing going on right over here in the edge. Let me see if I can find that spot on the board here again. You see these little bursty things. Because in this display here, really each horizontal row is looking down at the top of a spectrum trace, and the colors are essentially the amplitude of that. So you can learn a lot by looking at what's going on you might be able to determine what these signals are by looking at the repetition rate or looking at what they're doing over time, like that spread checking clock is doing there. So you can learn an awful lot about things. Let's say we want to go and really dig down into one particular signal, and I found one I was looking at earlier. See if I can get the probe positioned right here. So if we look on the spectrum, what we're seeing is this kind of elevated blue area. This is over 100 megahertz wide. Okay, and it's only there infrequently because it's lit up in the blue. Most of the time we're seeing the noise floor here, but I got this infrequent burst that's very broad banded. So we'll say, well, gee, what's going on with that? Well, if we look at the spectrogram, I can see these horizontal lines. Okay, and they're spaced at about 20 microseconds apart. In fact, another way to look at this, let's bring up a time domain view. Let's bring up, say, amplitude versus time. Bring that up here. And with that display, now I can actually see those little bursts. This is showing me RF power versus time in that direction. So if we look down here, we're looking at about 100 microseconds, so that's about 10 microseconds per division. So I can see that these little hairs are spaced out, spaced at about 20 microseconds per. So I know that's what's going on. So now I know the time domain nature of this signal. It's something that's occurring at about a 20 microsecond period. I can see its effect in the spectrum over time. I can see how it's interacting with other signals by looking at the spectrogram. Let's say we want to go hunting on the board to see what's going on with that. And we're just picking this all up with an antenna lane here. Okay. One of the things we can do is let's trigger on that. Okay. Now how could I trigger on that? There's a number of different ways. I could set up a little RF power trigger to trigger on that event. I could set up a frequency mask down in the spectrum and look at that. But the quickest and easiest way is something that we call a DPX density trigger. So I literally can right-click on the display and say, trigger on this. If I do that, I get this little box. I can position that box and move it right down into that area. So now each time the spectrum is crossing into that box, I'm triggering on that. And we can tell I'm triggering on it because if you look, say, even in the time domain, that waveform now is stable with respect to my little trigger indicator, which is way down there in the corner, a little T here in the corner. So I can see I've got a kind of a nice stable trigger. So now I know I'm triggering on that whatever event is causing that spectral energy. I'm triggering on that and giving you a synchronous display here. But now from a debug standpoint, what's really great is I can take the trigger output from the front panel here. See, I've got a BNC connection from that. I'm routing that up to channel 3 of my scope right here. So channel 3, there it is. That's my trigger output pulse. So now on the scope display, okay, I've actually got a triggered display here. So now I can take my probe, say from channel 1. I got my probe down here, and I was doing this earlier, and I found that let's go back up and look at display. I found that if I probe, let's see, I think it's right down here is a chip just underneath here. I probe the first pin of that, I can see a clock signal. And what I see on the scope is that this clock signal is synchronous, and you can see it's a stable display because I'm triggering on my trigger output pulse from the RSA. The waveform I'm getting from channel 1, if I can hold the probe on there, here we go, is stable with respect to that trigger. So that tells me that this clock that I'm looking at here is somehow related to this spectral event because it is synchronous to the trigger event that we were looking at there. So by using these kinds of tools and knowing the design of the board and what's going on here, you can now relate some of these spectral emissions and these transient type of events to actual signals and systems and things that are happening on your board there. So it may really help shorten your debug time and trying to understand where these transient EMI and emissions issues are coming from. So anyway, the tools we're using here is just a real-time spectrum analyzer. Gives you the ability to trigger on these signals, and then we're using a scope here to go look at time domain signals on the board and synchronizing them together with the trigger signal. So hopefully you can use this information to help you find problems on a circuit board you might be working on. Here's a quick little video to kind of show my QRP portable station Go Kit. Basically it's a backpack that my wife got for me. I had it embroidered with my call sign, W2AW. But it contains my portable station, all kind of self-contained. Right in the front pocket here, there's some various spools of coax and things like that, and some other wire. off in the side pockets over here, there are things like the charger for my batteries and some other DC power cords and things like that that you'd use to hook up to various power sources depending on where I go. The other pocket over on the side over here, this has got just other bunches of spools of wire and things like that to use as antennas or ground wire or whatever it might be. So inside are the antennas, the radio, and all of the other things that you need. So we open this up, see a number of different things here. So one thing inside this box right here, this is I've got a couple of spools of rope that I'll use to kind of toss over tree branches and things like that, a couple of different sizes and things like that. I just have them on these little cardboard spools. And then in here, this is a PAR end-fed antenna, and this is good for 40, 20, and 15 meters. Really nice, end-fed antenna is really convenient for portable operating because it only has to be suspended at one end. And I've used this, sat on the roof deck of a beach house and tossed it off the roof. I've thrown an end up into a tree, and it works really well. So that's one antenna. The other antenna that I bring with me, the box is a little beat up here. This is the called an MP1 by a company called Super Antenna. It's basically a kind of a manually adjusted, here's what we call a screwdriver style antenna. It's got an adjustable loading coil. There's a telescoping whip and a tripod and a little 80-meter coil here. So a nice little portable vertical antenna that works really well. Inside here is also my power source. I've got a pair of these 7.5 amp hour or 7 amp hour gel cell batteries. Everything with the power pole connectors on them. So I got one here, and there's a second one in here as well. So these I'll get several hours out of each of these batteries. So really good for portable operating. Also in here, this is a neat little device made by a company called Astroflight. This is a little power monitor. You stick it in line with the battery either when you're charging it or when you're using it. And it not only shows you the battery voltage, but it also shows you the total amount of amp hours that have gone either into the battery or out of the battery. So it'll kind of be able to monitor how much charge you've used or not used within your cell. So great little product there. And the rest of this is the radio box. In the radio box here, nice little handle, so mostly this is fairly self-contained once you have the antennas up. This box inside here is the radio and some of the other associated equipment. So this is the radio I use here. This is the ICOM IC703, 10 watt HF and 6 meter transceiver. Actually has a built-in tuner, which is kind of nice. Little bail at the bottom. I put a little piece of rubber hose on that to make it a little bit non-slip when it's sitting on the bench or wherever you happen to be using it. So very, very nice to use. Again, converted over to the power pole connectors. Got my